water, but we are using a solution, and it reacts with this silica and alumina, and the fly ash and slag will dissolve in that chemical and forms a product, a gel similar to CSH, calcium silicate hydroxide, but the chemistry is complex. I am not going to go into the chemistry of it. And so, but whatever product you are getting with this chemical composition is the binder, is the new glue without any cement in it. So, in a nutshell, what is alkali activator or geopolymer concrete? What we can say is it is a novel alternative binder material which can replace the Portland cement. And how do we make it? We produce it by alkali activation of industrial aluminosilicate waste, fly ash, slag, and calcine clay, or any material, naturally occurring, any material which has alumina and silica in it. You mix it with a solution. That solution is made out of sodium silicate and sodium hydroxide, or any alkali which has a high pH. You produce a paste very similar to Portland cement paste. When you mix cement plus water, it sets, it hardens, and that is the glue which can bind the aggregate together and produce the concrete very similar to a normal concrete. That concrete is known as alkali activated concrete or geopolymer concrete. If you go look at the very basic structure of this one using microstructure analysis, using scanning electron microscope, you will see the microstructure. This is a cross section at a very 10,000 magnification. You will see that it is very similar to the cement, hydrated cement, similar binding product. So it doesn't change any process, but you still have the concrete, a sustainable concrete without any cement. So why we need to use this concrete? This is also known as geopolymer concrete or alkali activator concrete. So mainly because of the sustainability issues, environmental benefits, utilization of the industrial byproduct, and lower CO2 emission. You make any of this geopolymer concrete, you can say 50 to 100% reduce the 50 to 100% of CO2 emission compared to an ordinary Portland cement. Here we are not even heating anything, we are not producing anything, so we don't need to spend any energy. So that's why we can save this much. Why 50 to 100% only? The alkali solution, like the sodium silicate or sodium hydroxide that we use to produce this one is going to be a little green. It will produce a little bit CO2. So if you are using it, this graph shows how much CO2 you can save. If you are using a solution less than 10% concentration, you can save up to 90% CO2, reduce the CO2 by 90%. And most of this geopolymer is made with those kind. Even if you go very high dosage of alkali, and if you are using metakaolin or something like that, which is more energy intensive material, you can still save 50%. So that is where the sustainability comes in. And is that the only thing, sustainability? If it is just the sustainability consideration alone, we may not be able to using this concrete. It has to perform very well. So a lot of research has been done on this geopolymer concrete, especially during last 10 years. And you can see even just in my group, 5 PhD students graduated in this topic. So meaning a lot of work has been done, and we have a lot of information saying that it is very good material, performance similar to a normal concrete, but better fire resistance, better durability, better corrosion resistance, But the application is very much limited now because we don't have the history of this concrete. Maybe we have history for 20, 25 years. We don't have durability things, and we don't have a standard specification. We don't have codes for using it. And we need more long-term data, especially the durability, long-lasting, how long it is going to stay, things like that. So that is the challenge we have to face. But I imagine in the next 10 years also, this concrete we will be realizing this concrete in the field. So when I say field, a lot of data in the academia and in the lab, we can make beautiful concrete without any cement. There are structures built using geopolymer. This is a building in Australia, in Queensland University, and this building is the Global Change Institute. In this building, all the floors are made with precast floor slabs with geopolymer, no cement in any of these ones. And similarly, you can see airport runway pavement. The runway is made out of 100% cement-free concrete, and the person standing over here is Professor Joseph David-Oitz from. He's a French professor. He is the one given the name to this concrete, geopolymer concrete. He is still alive, and he is still very active in making and promoting this kind of concrete. So I discuss the advantage of using this kind of concrete, and whatever else I am going to share with you is the data from our research group. And let me start with what is the chemistry. I don't want to go into the details of the chemistry that much, but very minimal for you to understand what is the difference, what is the chemistry by which we can create, what are the components, what is the importance. So the material you need to make is any byproduct that we have already discussed, slag, fly ash, or any aluminosilicate containing natural or byproduct material from other industries. So the chemistry of that material, we call it starting material, these SEMs, and is important. Some of them are crystalline, some of them are amorphous. Amorphous means it is glassy structure, it doesn't have an odor. You can check your material whether it is amorphous using X-ray analysis. If you have more amorphous material, it is much better for you to use that material. And the next important parameter is the solution that you are making. How do we make the solution? You have to have sodium oxide or potassium oxide or any alkali. You have to have some silica, dissolve the silica in that solution. And we normally say the proper chemistry of that solution, Na2O content and silica modulus. That is what we are going to say. And then you mix them, you get the binder, then you can decide like cement to water cement ratio. We call it water to cement ratio. Similarly, here we call it solution to binder ratio. The ratio of the solution to the material, that is the solution to binder ratio. You can, like in a precast industry, you can heat cure it, you can cure it normally, and when it start reacting with this material and the solution, it start giving off heat. The temperature will increase. All the reaction between this is exothermic. And if I can measure the heat emitted from this reaction, I will be able to gather a lot of information about my concrete, the strength, the setting time, the workability, all those things. So what we normally do is using a very high-tech box where it is called isothermal calorimetry, and we can put the paste inside this chamber and we can measure very accurately how much heat is evolved while it is reacting. Once I collect that heat, then this is heat collected similarly to a similar heat evolution from a Portland cement, the normal, typical, I am going to call it OPC, ordinary Portland cement. So when you mix water and cement, you will see a very large heat evolving initially for few minutes, 15 minutes. Then you have a very flat region for your hydration curve. We call it induction period. Then you will see a hype, an acceleration stage, starting with the initial set of your cement, ending at the final set of your cement or concrete, and then slows down. This is called the deceleration stage. So any cement reacting with water, we call it hydration. It has several stages. And if, as a concrete engineer in the site, you normally know what is happening here. So in this period called the induction period, where no heat is happening, for a normal Portland cement, it is around 2 to 3 hours. This is the time where you do all the mixing and transporting the concrete to the site in a concrete truck. It shouldn't set or harden in the concrete truck, and then within these 3 hours during this induction period, you are going to pour it, finish it, complete all the work, and by initial set, when it start reacting significantly cement grains, that is the initial set, and final set is you can walk over your concrete. This kind of data is very, very important whenever you develop any kind of new cement or new concrete. So here I am showing a similar curve. This is the black curve is showing the 100% cement hydration, the heat evolved. Instantaneous heat with time. On the x-axis is the time, y-axis is the heat. And if you replace as a supplementary cementitious material, you get only half of that heat, because you are replacing the cement, it is with the slag. But if you use just the slag, 100% slag with the water, it doesn't react. There is no heat, it is flat. And you can also measure the cumulative heat evolved with the time. So here, this is the OPC paste. This is the SCM with 50% of slag, and this is 100% slag. In the water, they are not reacting. But these two, looking at the heat evolved, I can say this will achieve very high strength, very good strength with time. So you can correlate the total heat and the strength. So this is 48 hours. After 48 hours, if you take a chunk of the set hardened cement paste, if you look under the microscope, when I say microscope, scanning electron microscope at a very high magnification, what you are seeing is the structure of your CSH gel, the binder, the gray portion is your CSH, that includes some of the calcium hydroxide also, the white portion is the unhydrated cement. This is the glue which is binding all the aggregate together and giving you all the strength. So what is happening if I use just 100% slag and use an alkali solution to activate? So these are the two curves, the instantaneous heat or the reaction kinetics of your alkali activated system and the total heat evolved. Looking at these graphs, you will see similar heat evolved, similar total heat evolved. So the geopolymer is very similar to your normal concrete, but you are not using any cement. The final product, looking at the microstructural level, micro 10 to the power 6 scale, you will see this kind of reaction product. The composition is different from CSH, but you will have the binder very similar to your CSH. This is the chemistry you have to understand to produce, and this kind of curve will give you all the information you need to understand this material. So I will stop the chemistry part there, and then let's see what is the engineering properties of this kind of geopolymer in the engineering application. So let's start with the most important property. Concrete is very good in resisting compressive stress, weak in tension. So that's why in concrete, reinforced concrete, we use steel to take the tension and concrete to compression. So the compressive strength is very, very important. So looking at this graph, if you look at this graph, these are made from 3 different starting materials. Slag, the green one is the slags, the blue one is the class C fly ash based geopolymer, and the blue ones, these are the class F based fly ash geopolymer. Looking at the strength, this is the 28-day strength. You can see a very high strength, 120 MPa is very high, ultra high performance concrete. And see, if you, this is a 5% Na2O content in the solution. If you increase that one, the strength will increase from 120 to 165 for slag based geopolymer. And if it is fly ash, it is 60. And we don't need this kind of strength for a normal application. You only need maybe 60, maximum 20 is the typical concrete that we can normally use for any construction application. So why I am showing this high strength is you can change the concentration of the solution and go with the required amount of your strength. So here you can create a design chart, okay, with a different combination of the solution, the Na2O content and silica modulus, and come up with the strength. So any person who doesn't have a knowledge of this solution and things like that, they just wanted to create a concrete with 40 MPa. So they go here and they can go find how much Na2O I need in the solution, how much, what should be the silica content. I can go to this chart and come up with the mixture proportion. You can also do that kind of evaluation. You can, using the design of experiment, you can come up with you are seeing here the setting time of your concrete, the workability or the strength. You can overlap all of them in that contour map, and then you can choose the concrete with the right setting time, right strength, and all those things. So this is different geopolymer material made from different materials, and what you are seeing is the properties will significantly change with the solution concentration of the material. So we have seen the compressive strength. The next property is the tensile strength. The tensile strength in US, how we find the tensile strength is using indirect testing like Brazilian test or split tension test. So if you do that one on this material and plot, this is the tensile strength versus compressive strength versus split tensile strength. So if you plot that one, this is the kind of data or model you can create, and you can get the equation and find out what is the tensile strength of this concrete. And typically for a Portland cement concrete, you can see here the Portland cement is somewhere here, and the alkali activated or geopolymer, it is approximately 20% of the compressive strength. It is slightly higher end of the tensile strength for this kind of material. And so we have seen the tensile strength. Now what about the modulus of elasticity? Another important engineering property of an engineering material or the concrete. What you are seeing is a typical compressive stress strain capture here. This is a fly ash based geopolymer, the red curve. 2 different mixtures, fly ash, both of them are fly ash. This is 2 different mixtures of OPC concrete. What you are seeing is here, the toughness of the material is slightly lower compared to your normal Portland cement concrete, but the elastic modulus is very, very similar. If you go to the slag-based, ground granulated blast furnace slag-based geopolymer, you will see similar test results. And again, the very good modulus of elasticity, again, the toughness or the brittleness increases with this kind of geopolymer. So we have option to reduce increase the toughness if you wanted to, using adding polymers or fibers in this concrete. You can do that in the geopolymer concrete as well. So, sorry. I am so sorry. I didn't switch off my phone. So any material, when you use it as a concrete in the field, we not only want a very good strength and initial properties, we want very good durability, long-lasting concrete. If you are designing it for long period of time, 50, 100 years, I know recent accidents in Cochin and other places, the concrete is failing and things like that. We don't want things to happen like that. So we want very long, durable concrete. So how is this concrete with respect to the durability? To show the importance of this concrete, I am taking some of the extreme conditions here. So what we have done is we made this geopolymer concrete and we soaked it in acid solutions. Acid is a very, very aggressive environment for any concrete. This is a Portland cement. You can see in this photo, in this photograph, OPC concrete or a mortar sample. It was exposed for 90 days in the sulfuric acid. It is just a mushy material once it is done around 75-80 days. But look at this geopolymer concrete. The integrity is still there. It did not dissolve. If you cut that one, you will see that the acid did not penetrate that much into the concrete and the cement did not leach out. The strength, you can also find the remaining strength of this concrete and plot it in here. That is what I am showing, the reduction in the strength with the time. This is your OPC concrete, the black one. The strength reduction is significant, but the geopolymer concrete, the strength is still keeping. It only lost around 20% in soaking in a very high, strong acid. Whether it is sulfuric acid, acetic acid, similar results, you have the same resistance of this material, very strong, like a ceramic material. What about the corrosion of steel in this kind of concrete? Corrosion, all of you know what is corrosion. We use reinforced concrete, the rebar, when it is come in contact with chloride or carbonation, it will rust, it will expand, it causes cracking of your concrete. So the corrosion, how good is the corrosion depends upon how much chloride is being penetrated into that concrete and reached the steel. So if your concrete is very good, low diffusion, you won't have chlorine reaching the steel and producing that kind of corrosion. So for this kind of concrete, the diffusion is significantly, many of them significantly lower than the OPC concrete. So it is going to protect your concrete very well, the steel, from corrosion. Also, we can measure different parameters like resistivity of your concrete. Higher the resistivity, better the protection for steel corrosion. So this concrete is very good in that aspect as well. In addition to this chloride and acid this concrete is very good in resisting freeze-thaw durability in areas where you have very cold temperature like North America, where I live here in New York State. We have a lot of snow, ice, and things like that. The concrete will freeze. The freezing and thawing resistance of this concrete is very good as well. But there are some additional areas where we need more research, long-term data to use this material widely. So I'm going to very briefly discuss some of the issues in this concrete as well. So the workability and setting time of this concrete, sometimes it is depending upon how much alkali you are using, what is the starting material. You may have very fast setting concrete. So that, and in typical concrete mixtures, what we normally do is we kind of control the setting time using admixtures, and any admixtures available in the market doesn't work with this kind of concrete. So we need to develop more of the admixtures that work with this kind of geopolymer concrete. We need to upscale, making a large amount of concrete. We need to put in place regulations and policies and logistics to make this concrete. Also, you can go with a very low dosage of the alkali. Sometimes you may not get enough strength. So you can use additional processing using other techniques like nanotechnology, using nanomaterials. You can enhance the strength significantly with low concentration of the alkali. That is also an option. Another issues researchers are finding a lot of contradicting data. How does it, what is the volume stability of this concrete? So volume stability we normally call shrinkage. This is happening when you have a concrete, when you make a concrete, when it dries, the water is evaporating from this concrete. When the water is evaporating from the fine pores within the concrete, it causes some capillary stress inside that causes tensile stress in your concrete. When the tensile stress is due to the capillary pressure is higher than the tensile strength of the concrete cracks. So typically, the concrete reduces in size, that is called shrinkage. So we can easily measure the shrinkage by monitoring the length of a concrete prism. And if you do that one for geopolymer concrete, this is the results. This is a typical OPC concrete. You get around less than 800 microstrain reduction in the size of your concrete. But in geopolymer, it is slightly higher. So you may have to process it differently, you may have to cure it differently, or you may have to open it after a certain period of time to reduce kind of that shrinkage. That is also, there are remedies, but it is not perfect. We need more information, long-term data on stability. Similarly, another durability issue is alkali-silica reactivity. Alkali-silica reaction, or ASR, is a very common problem. We used to call this as a concrete cancer before. Why? If you are using an aggregate, this is an aggregate, that aggregate is, if you don't have good quality aggregate, they may have some amorphous content in the aggregate itself. That aggregate will react with the alkalinity of your cement and produce a product which we call it ASR gel. That ASR gel will absorb water and it expands. When it expands, it cracks all the aggregates inside the concrete, and the manifestation is the cracks like this. So what is the resistance of this geopolymer concrete to ASR? We are seeing a good resistance. This is how we measure the expansion of the sample, concrete sample, and what we are measuring here is the expansion, and if this expansion is lower than certain limit, it won't. It is not susceptible to ASR. Some of these mixtures are showing some expansion. That means we need additional data. That is where a lot of research is going on, and we need to resolve that also. So with this, what I have done is I have shown you a new technology. I have discussed the benefits of this concrete, sustainable benefits. I have discussed the good performance of this concrete, and also the issues with this concrete. So with that, I just want to summarize my talk by giving you a couple of points emphasizing the sustainability of this concrete. This is a completely cement-free concrete. You can save a lot of CO2 emission if you use it in the field. The engineering properties are very good, but not widely being accepted in the field, mainly because we don't have long-term data, we don't have codes, specifications. We need all of them to start using it in the field. It needs some more additional studies in controlling the setting and workability. We need more data on the long-term performance, but you can use any industrial waste, any material available, naturally occurring material for making this concrete without using the cement. Now, I just wanted to add one more remark with respect to the Indian aspect, the scope of this kind of material in India. So in India, we produce around 220 million tons of fly ash as byproduct in thermal power plant, because we have a lot of coal-powered thermal power plants all over India. And to that amount, million tons of fly ash, that is the same amount of cement being produced in India. So you are producing 220 tons or million tons of cement, you are emitting 200 million tons of CO2 to the environment. Can we reduce that significantly? The 78% of the fly ash being produced in India is being used in the cement manufacturing or in replacing the cement in Portland in concrete. But 48 million tons is still dumped in the landfills, and we have scarcity of lands, we have environmental issues. Can we use that much of waste? Yes, we can. If you adopt a geopolymer technology, we can use this material, and we don't have to dump it in the landfills. And not only in concrete, can we make the clay bricks? You may be able to replace it with geopolymer bricks. So I don't know. Those are all options that we can adopt in India. So with that, that's all I have. And thank you again for the organizers and the speakers for listening, and also giving me a platform to introduce this topic in this conference. Thank you, and I will take any questions. I hope there will be a few minutes for discussion. Thank you.
Thank you, ma'am. The session is open for discussion. Those of you watching the YouTube channel can also post their doubts in the chat box. It will be clarified here by the host.
Hello.
What are the scope of studies in this area? So any material is required.
Can you repeat? I didn't hear initial part. Your mic was muted.
Okay. Ma'am, the fly ash means there is a chance of delay in the setting time of concrete.
Mm-hmm.
So fly ash, it's a material which delays the setting time of the concrete. How to improve this one setting time of the concrete?
Okay.
Is there any other material is there? That's the main disadvantage of using this type of fly ash.
Okay, fly ash, if you are using it as a replacement, if you use at a high dosage, it will delay the setting or the hardening, mainly because we are replacing the cement. It has to wait until the calcium hydroxide is being released and form the reaction. So that's why there is a limit for that. You cannot replace more than, if it is a class F fly ash, you cannot replace it more than 20%. How we do it, if it is a replacement, we reduce the water cement ratio significantly, and that will improve the setting time. You can also use set accelerating admixtures, but in the case of geopolymer, most of the time you have very fast setting mixture, because you are not only using the water, you are using the alkali solution. So the material is reacting very fast. Typically, we have to delay the setting, not accelerate in the geopolymer concrete.
What about the class C fly ash? In geopolymer, we can use that one. No?
Yeah, we can use both class C and class F. In class C, you have calcium in it, so it is even more fast setting compared to class F fly ash. There may be a little bit delay in class F, but class C is better with respect to setting. And sometimes you have premature setting if you are using class C with a very high dosage of alkali.
Okay. Thank you, ma'am, for your.
No problem.
Any others?
Feel free to ask question in Malayalam also. I can answer in Malayalam if you prefer that way. That's not an issue.
Students, from the faculty side, any question? So our chair, one of our chair, Anjana Ajit.
Hi, ma'am.
Hi.
Myself, Farzana. Okay, let me ask a doubt. And what about the heat of hydration reduced by using this type of admixture, and how it affect the cracking?
Yeah, that's a very good question. So you can see that when geopolymer concrete, the heat evolved is it is being evolved in a very short period of time in the beginning, like maybe 1 hour, 2 hours. And the total heat is much lower than a normal Portland cement hydration during that one. So that will reduce the cracking. If you are talking about the thermal cracking due to the heat, the difference in the heat, it will reduce the thermal cracking because the total heat evolved in this geopolymer concrete is much lower than a typical cement, OPC cement.
So,
okay, thank you, ma'am.
No problem.
I'm also alumni of Semi College. Glad to meet you.
What is it?
She's an alumni of the college.
Oh, really? Okay.
Yeah, 2020 passed out. Thank you.
Oh,
2020
okay.
passed out.
I graduated
Thank you.
94, so it's very long back.
Okay. Thank you, ma'am.
Any other questions from the MTech students?
Hello.
Okay. Now.
Hello, madam. My question is that you said that alkali solutions are used for this, no?
Yes.
And so the curing is not possible in water, right?
One of the advantage of this geopolymer is you don't have to cure it like a normal concrete.
Steam
You
curing
can
is
just
there, no?
you can do heat curing, you can do just leave it in the lab or in the ambient conditions. The water is not taking part in the reaction, so you don't need water for continuation of the hydration. So you don't have to do it. You can do typical curing if you can soak it in water also. That is also fine, because if you formulate your mixture properly, enough alkali in the solution, the alkali from the concrete is not going to leach out. It will be part of the new product forming the binding gel. It is not going to dissolve in water. So not a problem at all. But one of the advantages, you don't have to cure it in water for this kind of concrete.
So the
Now-
normal curing will affect the strength, no?
Not at all. It doesn't affect the strength at all. It will remain the same. Some of the water curing, depending upon if it is slag or things like that, you can prevent cracking if you are soaking it in water. Normal curing can be done. It is very similar to your Portland cement concrete, no difference. One of the issue in concrete making is the inadequate curing in your concrete that causes cracking and other low durability. So this is more forgiving, this geopolymer concrete. Even if you don't cure it, soak it in water, spray it in water, it still gains strength with time.
Will it be more expensive compared to the normal concrete?
Very good question. So the price of this concrete is from 80%, can go anywhere from 80% of normal Portland cement concrete to 140%. So if you are using a byproduct like a fly ash, you don't have to pay anything. And using a low dosage alkali, you can make a concrete cheaper than normal Portland cement concrete. But if you are using a metakaolin or calcine clay, where you need to heat the clay and produce that aluminum silicate and use a higher dosage of alkali, then you will be in the higher end. So it is up to you. With respect to the price, you can get a similar price, but I would say the price is not the important issue here. The sustainability we are achieving through this concrete is the biggest thing. So slightly expensive concrete, even if it is not, but if it is expensive, still it is much more better product with respect to the sustainability and CO2 emission, considering that aspect. Thank you.
Thank you, ma'am. Now I call upon Dr. Seena ma'am to thank our keynote speaker.
On behalf of the Seaside 2020 coordinates, I would like to extend my sincere thanks to Dr. Sulabha Pithamparan, Professor, Clarkson University, USA, who accepted my invitation and gave her wholehearted support to the event. She also readily responded to all my correspondence in spite of her busy schedule. Madam delivered an excellent talk on alkali activated concrete, a sustainable alternate to Portland concrete, and enlightened us. I am absolutely positive this detailed lecture is going to be of great knowledge to our students. Thank you, ma'am.
Thank you very much. And once again, thank you, Seena, for all the communication. And thank you very much for giving me an opportunity also to see you guys and also just share the new kind of concrete in our country also. Thank you very much.
Convey my regards to Dr. Ajit Achudin sir also.
Yeah, Lal sir
Sir, no?
also. I saw Lal sir several years back. Lal sir's brother is my classmate, and my husband is alumni from Thrissur. That's how I ended up here talking today. Thank you, Lal sir, too.
Thank you, Sulafa ma'am. Thank you, Seena ma'am. Now I call upon the distinguished chairs, Dr. Anjana Shantakumar and Dr. Seena P. A brief intro. Dr. Anjana Shantakumar is a professor of the Department of Civil Engineering and Government Engineering College, Kozhikode. She received her MTech and PhD from NIT Calicut. She has professional experience of 22 years and 6 months in teaching. During this tenure, she served as head of department also. She has published 8 journal papers and 5 conference papers. Her research areas are structural design, fiber reinforced concrete, geopolymer concrete. About Dr. Seena ma'am, she is a professor in the Department of Civil Engineering at Government Engineering College, Thrissur. She received her MTech and PhD from NIT Calicut. She has professional experience of 20 years in teaching. She has published international and national journals and conference papers. Her research areas are structural design, shear wall, and composite concrete. Welcome, Anjana ma'am and Seena ma'am. Now, we will be moving on to the presentations by the participants. I call upon the first participant, Mr. Rahmatullah Naufal.
Before that, Sulabha ma'am, could you please stop sharing? This one.
Yeah, I did.
You can join in the session, ma'am.
Yeah, I may. It's 12 o'clock midnight here.
Okay,
Maybe
okay.
I
you
will stay a little bit and then I will log out.
This session is related to mechanics of materials. Okay, let us start.
Mr. Rahmatullah Naufal, can presentation by Mr. Rahmatullah Naufal.
Respected dignitaries in the conference, respected coordinators of the conference, and dear participants, a very good morning, all of you. First of all, let me introduce myself. My name is Rahmatullah Naufal, and I am from Government Engineering College, Calicut, working as Associate Professor in Civil Engineering. So, here in this conference, I am presenting this paper of influence of copper slag and GGBS on mechanical properties of concrete. As we all are aware that the concrete, the materials required, the raw materials required for concrete construction is having acute shortage day by day. Here in concrete, about 70% of the volume of concrete is the aggregates, whether it is coarse aggregate or fine aggregate. So if we are using these materials from the nature, the availability of the resources is decreasing. In earlier, as we know that we are using the river sand as fine aggregate for concrete. Nowadays, it is banned in many of the states, so we will not get the river sand for construction. The another one that we are using right now is the M sand, that is a manufactured sand from the quarries. Manufactured sand, one from the land, river sand, one from the river. That is the only difference. Both are the natural resources. So this availability of this quantity is decreasing. So we have to think of an alternative for the materials for construction. So here I made an attempt for finding out the replacement of some materials in concrete so that we can preserve the natural resources as well as we can utilize the other material. So in that way, I used two materials for this work. The first one is the copper slag. This copper slag is the waste product from the copper industry, and the GGBS, that is a ground granulated blast furnace slag, which is from the iron and steel industry. So both are used for the replacement of fine aggregate and cement in construction. So normally this copper slag and GGBS are disposed to land for landfill and also maybe for the formation of roads and all. So we can now utilize this copper slag for the construction of concrete as fine aggregate. And also in this experiment, fine aggregate, that is river sand, is used for experimental work. River sand, 40% of the river sand is replaced with the copper slag, and partial replacement of cement, OPC 53 grade cement, is done with GGBS. And in my previous work,
Excuse me,
I
Naupal.
did replacement of copper slag, river sand with
me.
copper slag
Naupal on the slideshow
partially in concrete, and I got a value of 40% optimum replacement of copper slag so that I will get the maximum value of compressive strength, split tensile strength. And that is published in the paper ACC, Advances in Concrete Construction, in 2020. So from that, I started this work. That is by keeping 40% replacement of river sand with copper slag, and then the partial replacement of OPC 53 grade cement with GGBS, to find out an optimum replacement value in which I have to get the maximum strength and getting a good mix design also. So physical property evaluation is done for the concrete and materials, mechanical property evaluation is done, durability studies are also conducted, its elemental properties calculated by using this compositional analysis, and direct shear test is done to find out the friction of the particles, and ultrasonic pulse velocity test is also done. It is a non-destructive testing to find out the quality of the concrete. So here, the motivation behind is that the environmental issue plus the socio-economic impact. As we know that the indiscriminate extraction of river sand for construction leading to irreversible damage to the environment. Lot of issues are there, global warming, landsliding, flood, every issues are there because of this sandy mining, and also this M-sand also from the quarries also issues are there. And another issue is the disposal of the copper slag waste, the waste product generated from the copper industries. And if you are using this waste product to the concrete, it will have two advantages. One, it will preserve the natural resources, and the other one is we will have a good economical disposal of this waste. Okay. And in the production of cement, as we know that large amount of CO2 gases are released, and it will affect global warming, and so many issues will be there. So if you are replacing the cement with GGBS and all, it will lead to the reduction of the release of CO2 gases. And finally, save the Mother Earth through the environmental friendly alternative substitute for concrete. That is our main aim. So here the experiments are done by replacing the fine aggregate with copper slag and also cement with GGBS. And an optimal mix is calculated with a mixed design of M25 and M30, in which we are getting the maximum value for compressive strength, maximum value for split tensile strength, and also maximum value for flexural strength. That is the experimental part that I had done. Okay. So this is a quantity. From here you can see that about 7% of the CO2 gas is, greenhouse emission is there in the production of cement industry. And also copper industry produces 24.6 million tons of copper slag as waste every year, which is often not utilized properly or often disposed as landfill. So in the matte smelting process during the manufacturing of copper result in the production of copper slag, and also in the iron and steel industry, GGBS is produced. So these all are some pictures regarding river sand, GGBS and copper slag. So the first thing is that the material property. If you are using copper slag for this as fine aggregate, it has to be satisfied some criteria based on the IS code. So these properties are compared with the IS code and also fine aggregate. The first work done is the sieve analysis. As you know, what is the sieve analysis? The gradation. So after sieve analysis, this is the graph for sieve analysis for river sand and also for copper slag. And you can see the values. These values are exactly matching with the standards. So the gradation is okay. This is coming in zone 2, can be used for mass concrete. Another properties are the mechanical property where the gradation, specific gravity, water absorption, some values are there. Specific gravity, you can see that this will be little bit high, 3.9 to, sorry, 3.3 to 3.9. This is because in the copper slag, the iron content is more, about 50 to 51% is there. Due to that, the specific weight is also, or specific gravity is more in the copper slag. And to find out the good bonding between this copper slag material and the river sand, I had done the direct shear test to find out the angle of friction and C5 values. Okay. So these are the graph which shows the shear stress versus shear displacement, and the slope is drawn. And from here we will get the phi value, angle of friction. This is for copper slag and this one is for river sand. Okay. And the values are tabulated here. This is river sand value for angle of friction is 38.48 and copper slag 34.79. So you can see that these two values are comparable. So we'll have good friction. Another one is to find out the elemental properties. What are the elements present in the copper slag? Is there any reactive elements are there? Is it harmful to the concrete? Suppose if you're adding water and all, is there any other harmful reactions are there? For that, we must know what are the elements present in it. So this compositional analysis is done as semidax given is conducted. And these are the composition with the percentage values of the elements which is present. From this table, you can see that the Fe content, the iron is 51.42% is Fe content. And the second one is the silica, that is 39.88. So from this, we can, it clearly says that it mainly composed of silica and significant percentage of Fe. And these are some comparative properties of the cement and GGBS regarding its water absorption and specific gravity, etc. And after that, what I did is this M25 and M30 mix designs are done. And a particular mix ratio is calculated. Based on the mix ratio, the cube, cylinders, and beams are casted for 7 days. It is cured for 7 days and 28 days. And it is tested by using compressive strength by using compression testing machine, structural strength by using UTM, or you can test with structural testing machine, and a split tensile strength by using UTM, universal testing machine. So in this slide, you can see that for mixed design of M25, here what I did is the percentage replacement of copper slag is kept as constant 40% in fine aggregate, and an increment of 5% is then in replacement in cement with GGBS. Okay. For this replacement, the concrete cubes are casted for, and it is cured for 7 days and 28 days. So you can see that every increase in the replacement of GGBS, this value is increasing. For 30%, we are getting a maximum value for the 30% for M25 concrete. Similarly, for M30 design, the mixed proportion is like this: 7 days and 28 days of curing and the same percentage replacement. From the graph, we can see that for 30%, we are getting a maximum value of compressive strength. And this is for split tensile strength, in which this, cylinders are casted for a diameter of 150 mm and the length of 300 mm or 30 centimeter. And these cylinders are cured for 7 days and 28 days, and it is tested like this by using universal testing machine and calculated a split tensile strength for 7 days and 28 days. Same proportion, 40% constant for copper slag and also 5% replacement for GGBS is done. You can see the graph which shows the replacement percentage on x-axis and y-axis split tensile strength. This value is also having a maximum value for an optimal replacement of 30% GGBS. Okay. And for M30 mixed design, same proportion with same replacement. Also, we are getting 30% as the maximum value for this. Another one is to calculate what is the flexural strength of the concrete. For that, 150 mm square dimension of beam with a length of 750 mm is casted like this and cured for 7 days and 28 days, and then tested by using universal testing machine. So 7 days and 20 days, same percentage replacement I had taken, and you can see the replacement versus flexural strength is drawn like this. And for a 30% replacement also, in this case, we are getting the optimum maximum value also. For M30 also, same thing, same replacement. The mix ratio also different, is the same which is related to the previous one. And also you can see 7 days and 28 days curing of the beam For 30%, we are getting a maximum value in this case. So it is 30% we are getting maximum strength in these three cases: compression testing and the split tensile strength and flexural testing. Another one to find out what is the quality of concrete, what is the density or what is the model, what is the uniformity of the material in the concrete. I did this UPV, ultrasonic pulse velocity tester. It's a non-destructive testing method in which we'll get the quality of the concrete, the density of the concrete. So these are the standard, table which is available in the IS code, IS code 13311 1992, in which if you're having the pulse velocity within this range, we can say the concrete is having excellent, good, medium, and doubtful, like that. So this is the concrete cube that we have taken, and you can see the probes are fixed on the two ends, and the current is passed, or the electric pulse velocity. This pulse signal is passed from one end and it is received in the other end. And you can see that we will get the time passing for the signal from this end to this end. We will get the time here. We can measure the distance. So distance by time, we will get the velocity. That velocity we can compare by using the standard table, and we can assess that what is the type of the concrete, whether it is good, excellent, or medium, like that. So in that way, you can see that the replacement, same replacement proportion, we clustered the cube. And in that cube, you can see we are getting a value of 30%. We are getting maximum value, that is 4.84 kilometer per second. And here it is 4.97. Anyway, when we are replacing with the industrial waste, the velocity increases. That means the quality of the concrete or density increases. That is the meaning of it. And the next one is the rapid chloride permeability test, RCPT. It is conducted. This is the standard table for. Here what is done is sodium chloride and sodium hydroxide solutions are prepared into containers, and 2 leads are put like this, and it is placed on the two sides of a concrete small cylinder, and then the current is passed through this with 60 volt DC, and the dimension is 100 mm dia and 50 mm thick. That is the dimension for 6 hours, and for every half an hour we will be measuring the current passed through the concrete. And then after adding all these values, we will be finding out what is the total current which is passed during that particular time. And the total charge passed is determined. And these are the values for the, we did the same replacement percentage for M25 and M30 concrete with the same replacement. You can see that here initially when we are not adding this industrial waste, the chloride ion permeability is moderate. When we are adding this, replaced it, you can see that it is coming low. Low means the passage of current is low, means it is not porous structure. So the chloride ion ingress through the concrete. The rate of ingress of chloride into concrete depends upon the pore structure of concrete. So the pore structure is less. That's why the current value is become low. Okay. So you can see that this value is again after 30% increase. You can see that these values are increasing. This current is little bit increasing. That means that sometimes there will be a conducting material is there, or sometimes the gaps or the pore structure is increasing. That is the significance. And these are the summary. What is the reason why these values are increasing after a particular replacement percentage? So the result suggests that the physical properties of copper slag aids in increasing the workability of concrete and the fineness modulus, and also the specific gravity of water. All these values are increasing. And another thing is that this reduction in the strength is due to more than 40% copper slag is due to the change of total voids amount of the free water content. And another thing is that the addition of GGBS improves the particle packing. GBS can be used as replacement of cement because it contains the same oxides and undergoes the same hydration. So in conclusion, we can say that we can replace this material effectively in concrete. It will lead to the waste to wealth economy, and also it will preserve the natural resources, and we can dispose the industrial waste properly. Thank you. Thank you for giving me a chance for this presentation.
Next 3 minutes will be the question and discussion session between the chair and the presenter.
Anjana,
Okay.
Not audible. Now it's audible.
Okay, Naufal, it is a rare situation that one of my colleague is presenting and I am here to ask some questions.
Okay.
Okay. Now it is a very good paper
Thank
and
you.
let me ask one or two doubts about this
Okay.
presentation. That is,
Okay.
what is the significance of this direct shear test in properties, mechanical properties of cement or concrete, mechanical properties of concrete?
So here it is done that we are taking the copper slag for concrete. No, it's an industrial grade. So we must know the shape of the copper slag is not similar to the river sand. So the bonding between the material depends upon the phi value and all, angle of friction and all. That's why I've calculated this phi value for, and just compare the phi values of river sand with the copper slag. That's all, and that values are almost coming almost same. It's only
Okay.
because of the bonding. Yeah.
Okay, bonding actually, bond stress for concrete is found in a different manner. That's why I asked this. This
No,
is
no, not
from
not
this.
for concrete, madam. Not for concrete. It's only for the
Okay.
material. I think only
Okay.
for the just for comparing copper slag with river sand. That's all.
Okay. Then what about the fineness modulus of this copper slag? Is
Finest
it
modulus of
comparable to river sand?
compared to river sand, it is about 15% more.
15% more.
Yeah,
Okay. Still, it is within the limits.
yeah, within the limit. Yeah.
Okay. Now, is there any disadvantage of this combination, this copper slag being എന്താണ് copper slag എന്ന് sand ആയിട്ടല്ലേ replace ചെയ്യുന്നത് and
Okay.
then GGBS with respect to cement.
Yeah.
In this combination, is there any disadvantage coming into picture while it is acting together as a concrete mixture?
Not that. The only thing is that I find out the reaction, reactive materials in copper slag. Since it is 51% iron content is there, it is not reactive. But the thing is that the water absorption of the copper slag compared to river sand is very less. That is another issue. Suppose if we are adding more copper slag, then the water cement ratio will affect. Like the water absorption decreases when we are adding more copper slag. So what will happen is it will increase the pore structure in concrete. So if you are using the correct design, then it's okay.
Okay, Naupal, thank you.
Thank you, madam. Thank you.
Naufal, you have presented a very good topic which
Thank
is
you.
relevant to the current scenario.
Thank you,
And
madam.
you have explained all the properties of the materials and mechanical properties and other experimental results also.
Thank you.
It's quite sufficient. Now, one question from Mr. Sujit Kumar asked, what about bulking properties as compared to sand?
Bulking properties compared to sand is very less.
Okay. Bulking is less.
Yeah, bulking is less.
Okay. Did you check that one? Bulking properties?
Yeah, I checked that one.
Then we can move on to the next presentation, okay?
Thank you, madam. Thank you.
Thank you, Mr. Rahmatullah.
Thank you, madam.
Now I call upon Ms. Chitra KS, next presenting author, paper ID 253.
Chitra KS, are you there?
Yes, ma'am.
Okay. Your pre-recorded video is presenting now.
Yes, ma'am.
Wait for 1 minute. അത് ഇവിടെ നീ മ്യൂട്ട് ചെയ്തില്ല, അതുകൊണ്ടാണ്.
അല്ല, അത് ഷെയർ ചെയ്യുമ്പോൾ ഷെയർ പറഞ്ഞിട്ട് കൊടുക്കണം.
നിങ്ങൾ അങ്ങനെ ചെയ്യാൻ അതാണ് ഇവിടെ അങ്ങനത്തെ വിഷയം.
Regret the delay caused.
Warm regards of the day. I'm Chitra KS from Vidya Academy of Science and Technology, Thrissur, aiming to present the idea on the economic feasibility of fly ash and ground granulated blast furnace slag-based geopolymer concrete. Co-authors of the paper are Anand Rajkunath, Binoy Thomas, Harismita A, and Professor Deepa Mohan. This is a part of our BTech final year project. It is a well-known fact that carbon dioxide emission is increasing day by day, and it can cause a huge impact on Earth. The concrete, the second most consumed product all over the world, and cement, which is its main constituent, can contribute 7% of global carbon emission. So it is very much necessary to introduce an alternative binding agent, which should be sustainable. So geopolymer concrete is one such solution, which is more eco-friendly. Now, what is meant by geopolymer concrete? The term geopolymer concrete was introduced by Davidovich in the year of 1978, and it is also known as an inorganic polymer. This can act as a binding agent in concrete. How this binding property happens? It is by the alkaline activation of aluminosilicates. Thus, it can replace the ordinary Portland cement in the concrete. As this geopolymer is obtained from byproducts of industries, it can be eco-friendly. How? As it is a solution to the problem of waste disposal from the industries, as well as it also reduces the carbon dioxide emission from cement. Now, what constitutes the geopolymer concrete? It constitutes a source material which is rich in silicon and aluminum in amorphous form. It can be base materials such as fly ash, metakaolin, GGBS, etc. And these materials are activated by alkaline activators, which is a mixture of sodium hydroxide or potassium hydroxide with sodium silicate or potassium silicate. Along with this, it constitutes water, coarse aggregate, and fine aggregate. Now, coming to the objective of this study, it is to compare the cost of conventional concrete mix, that is the OPC concrete mix, with geopolymer concrete mix of same grade. And the materials used for this study are cement, Dalmia brand OPC 50 grade, coarse aggregate, fine aggregate, GGBS, fly ash, water, activators, a mixture of 8 molar of sodium hydroxide and sodium silicate solution. Now, this is a picture showing the materials we used for the geopolymer concrete, that is GGBS, fly ash, water, fine aggregate, coarse aggregate, and the activator. It's a mixture of sodium hydroxide, 8 molar, and the sodium silicate. Now, coming to the methodology of the study. After conducting many preliminary tests for the material properties such as specific gravity, fineness, water absorption, standard consistency, setting time, etc. of the materials, we had formulated the mix design for the conventional concrete mix as well as the geopolymer concrete mix with various proportion of fly ash and GGBS mix. And we had conducted the workability test as well as the test for strength. And from this strength test, we had obtained an optimum mix for the GPC mix, that is with the maximum strength. And it is obtained as 50:50 ratio of fly ash and GGBS, which gives the maximum strength. And from this analysis, we had taken this optimum GPC mix and the conventional M25 mix for the cost analysis, for finding out the economic feasibility of this material. So the slide shows the mix design of the optimum mix of 50:50 ratio of GGBS fly ash combination. We had conducted the experiment for a grade of M25. We had taken a water cement ratio of 0.5 and water content of 210 liters. We had used 20 mm coarse aggregates and zone 2 fine aggregate. And we obtained the quantities for 1 meter cube of concrete, such as for fly ash, GGBS, and coarse aggregate and fine aggregate. We had also obtained the quantities of sodium hydroxide and sodium silicate by taking the activator is to binder ratio as 0.35 to 1 and the sodium hydroxide to sodium silicate ratio as 1 is to 2.5. And we obtained a slump of 70 mm for this mix design. And similarly, we had also calculated for the M25 conventional concrete, and the quantities obtained for 1 meter cube of concrete is tabulated here along with the GPC M25 optimum mix. Now coming to the cost analysis, we have conducted the cost analysis for the optimum GPC mix and for the conventional M25 mix of 1 meter cube concrete. And for this, we have taken the cost from various sources, and the sources are given, that is fly ash from the Neptune Ready-Mix Concrete Private Limited in Mundu, Thrissur, and GGBS from JSW Cement Limited in Ernakulam, fine aggregate and coarse aggregate from the Project Information and Cost Estimation Mode 3 2016 Kerala, and NaOH and sodium silicate from the Pentagon Chemicals Chennai, and the cement of Dalmia 53 grade. And coming to the results and discussion. After conducting the workability test, that is slump test, we had obtained a slump of 70 mm for both GPC and the GPC optimum mix and the conventional M25 mix, thus saying that it is medium workable. And coming to the strength test results, for the 28-day compressive strength test, we had obtained a strength of 30.62 Newton per mm square for the M25 conventional concrete and a value of 53.29 Newton per mm square for M25 GPC optimum mix, which is very much higher than the other. Then for the 28-day stick tensile strength test, we obtained a strength of 2.96 Newton per mm square for the conventional M25 concrete mix and 3.77 Newton per mm square for the optimum GPC M25 mix, which is also higher than the other. And coming to the cost analysis we had done for the 1 meter cube of concrete, is the analysis is shown in this table. In this table, the first two columns shows the materials and its unit price. That is, cement costs rupees of 7.5 per kg, fly ash rupees of 1.5 per kg, GGBS rupees of 4 per kg, fine aggregate rupees of 1,303.77 per meter cube, coarse aggregate rupees of 1,403.77 per meter cube, NaOH flakes of rupees 45 per kg, and sodium silicate of rupees 18 per kg. And the third column shows the 1 meter cube concrete cost for the M25 conventional concrete, and we obtained the total cost of 4,702.56. And the last column shows the cost of GPC optimum M25 mix, and we obtained a total of 4,860.54 rupees. And this shows the graphical representation of cost analysis. And from this, we can see that cost of GPC of M25 optimum mix is higher than that of the M25 conventional mix. So we can conclude that there is an increase of 3.36% of cost for the optimum GPC mix than the conventional mix. But looking forward to the strength characteristics or the strength parameters of the GPC, we can say that GPC is twice than that of the conventional concrete. And looking towards the other benefits of GPC, that is, it works as a solution to the solid waste disposal, as well as it can control the carbon dioxide emission from cement. Therefore, we can say that GPC is still economical than the conventional mix. Therefore, we can say that industrial waste materials such as GGBS and fly ash can be utilized for the complete replacement of cement in concrete. Thus, I conclude. These are the references we had studied. Thank you for your time and attention. Thank you.
Anjana ma'am and Seena ma'am, the questions can.
Okay, Chitra. It was a good topic. It's a need of the hour. Then let me ask one or two questions. Why this term geopolymer? You are speaking about geopolymer concrete. Why is it known as geopolymer?
Hello. Hello,
Yeah.
Miss. Can you
Okay.
hear me?
Yes, you are audible.
Geopolymer means it's a type of concrete which is made from the byproducts of industrial products, and it is alkylated by the activator such that it causes its binding property.
Okay, are you adding any polymers in that?
So this because when these activators are added, the polymerization occurs, which causes its binding property.
Okay. Then, regarding the cost of this geopolymer, is there any cost? This fly ash as well as GGBS is a byproduct. Both these products are byproducts from the certain plants. So, how can they?
Yes, both these fly.
Is it a transporting charge?
Ma'am, can you please repeat?
Both these are byproducts. You have shown one table regarding the charges of the cement, fly ash, GGBS, like that. Is it not? In
Yes,
that,
ma'am.
for fly ash, I think it is rupees 4 per kg, something like that you have shown. Is it a transportation charge?
Yes, ma'am. Yes, we had taken from a company called as JSW, and the price is according to their transportation, etc.
What is the price for 1 ton of this fly ash? So fly ash means material cost is 0, only the transportation cost. Isn't it? From where you procured this one, JSW? From where? In Kerala only or outside?
JSW Cements in Ernakulam. From their factory we had taken this. Yes.
That price is inclusive of this one, transportation charge. What is the grade of fly ash you have used?
It's Class C.
Why can't you use Class S?
We can use, but we had chosen this one for this experiment. You can use both.
Is it matching with the composition of the cement?
Yes.
Then okay, Chitra.
Thank you,
Thank you, Ms. Chitra K.S. Next presenter is Mr. Steve Matthew, paper ID 486.
Good afternoon, respected faculties. I am Steve Matthew. I'll be taking a presentation on a methodology for effective use of materials in concrete paving work. Concrete paving blocks have been extensively used in special problem areas where other forms of pavement are less durable. They were individual blocks of various sizes and patterns that laid between edge restraints on a thin bed of sand. In India, concrete paving blocks have been used for over 30 years, particularly in parking lots, footpaths, gas stations, and for military purposes, etc. These concrete paving blocks are flexible, aesthetically appealing, reliable, and cost-effective, and require less maintenance if they are laid effectively. Objective. Our aim is to develop an optimized mix design for paving blocks by considering both quality and economy. Methodology. The first step is a study of specific prerequisites for mixed design of paving block. Then, selection of materials. Based on the selection of materials, basic study of basic material properties for the selected materials. By considering packing density, principles of packing density method, optimization of materials, and finally, developing mixed design using packing density method. Specific prerequisites for mixed design of paver block. These are the IS codes required for the manufacturing process of paver block. Mixed design of paver block is mentioned in IS 10262-2000. Grade and thickness of concrete is mentioned in IS 15658-2006. Characteristics of aggregates is given in IS 383-1970. Cement type and water cement ratio are provided in IRC SP 63-2004. Water quality is mentioned in IS 456-2000 and IS 15658-2006. Selection of materials. The materials are selected based on careful observation and study of properties. The raw materials selected for the mixed design are cement of grade of OPC 53 grade, coarse aggregate of size 12.5 mm, 10 mm and 6.25 mm. Fine aggregate is selected as M sand. Traffic condition as medium, for which the grade of design will be M40. Water cement ratio is selected as 0.38 based on IRC SP 63-2004. Basic material properties. For doing packing density method, the aggregates have to be tested for specific gravity and bulk density. Table 2 gives the specific gravity of aggregates. For coarse aggregate, the specific gravity value is 2.67 and for fine aggregate, it's 2.76. Table 3 shows the bulk density of aggregates. Here, the bulk density is calculated in both loosely packed form and compacted form. The values are shown in the table. Optimization of materials using packing density method. Packing density method is used to optimize particle packing density of concrete. The packing density method maximizes the concrete material packing density by selecting perfect measure of different aggregates to fill the voids, allowing a denser and firmer structure. Higher degree of particle packing density leads to minimum voids, maximum density, and thereby resulting in fewer cement content, and also less water content. Table 4 shows the work density for different proportions of aggregate. Here, the bulk density for different proportions of coarse aggregate is detailed. First, we are starting by 50% for 12.5 mm, 30% of 10 mm, and 20% for 6.25 mm. Then 80% of 12.5 mm, 5% of 10 mm, and 15% of 6.25 mm. Total 11 aggregate proportions. Then the weight for loosely packed and compacted aggregates are taken, and then the bulk density for loosely packed and compacted form is collected, and finally, using these results, bulk density coefficient is calculated. The proportion with maximum bulk density coefficient is selected. Here, it is 17:15:15, giving a maximum bulk density coefficient of 0.937. Mixed design using packing density method. The mix design is calculated using packing density method, and the important formulas used for calculating mix design are given below. Packing density equal bulk density into weight fraction by specific gravity. Total packing density can be obtained by adding packing density of coarse aggregates and packing density of fine aggregates. Void content in percent volume equal 1 minus total packing density into 100. These formulas are used throughout during calculation of mix design. Results and discussions. These are the final mix proportion we obtain using packing density method. The final mix proportions for cement are given below. For cement, it is 417 kg per meter cube. Fine aggregate, 767.013 kg per meter cube. For 12.5 mm coarse aggregate, 805.364 kg per meter cube. For 10 mm and 6.5 mm, 172.578 kg per meter cube. The mix design obtained is for M40 mix design, and this method can also be used for obtaining other mix designs. Conclusion. The packing density approach optimizes the concrete particle packing density and produces a dense and firm structure, thereby reducing lighter material in turn. The above approach can also be used to achieve a mix design for material replacement. These are the references. These are the references we used for our study. Thank you for your attention.
Session is open to the chairs for questions.
Okay. How do you test this?
Hello, ma'am. Sorry.
Can you hear me?
Yes, ma'am.
How do you test these paving blocks? What is the type of test conducted for this paving blocks?
Ma'am, we will be conducting compression test, tensile strength, split tensile strength, compression strength test. Basically, we are going.
Okay, tell me. How do you conduct split tensile test? Is it like a cylinder?
Yes, ma'am. It's like a cylinder.
Paving block.
Paving block, yes.
What is the shape of that?
Ma'am, no, sorry, ma'am. It's like a cubical shape. We will be testing cubical.
How can this split tensile test be conducted on cube test or cube specimens?
Ma'am, just for knowing the value. Ma'am, for split tensile strength, we will be using cylindrical shape. And for the rest, we will be using cubical shape.
Actually, what is the shape of this paving block that you have made?
Ma'am, it's rectangular shaped. Ma'am, we didn't conduct any test because of this COVID pandemic. We are just proposing the methodology for this design.
Okay, Seena, I can continue.
So what is the guidelines for this methodology? From where you obtained the guidelines?
Ma'am, it's a journal in packing density method, a methodology for using packing density method. It's a journal.
Oh, using their guidelines, sir?
Yeah, yes, ma'am.
You got the optimum this one mix design.
Oh, okay, for
so how much increase made in the bulk density? For the conventional concrete, how much you got? What's the value of bulk density you have got?
Ma'am, it's like about 10% increase.
So you got some value about 1,600 and something, no?
Yes.
Then for the conventional concrete, it is around how much? So
1,500.
usually, it's usually around 1,500. So
500.
10% increase is made by using this packing density method.
Yes, ma'am.
Okay, which we can use for this one conventional concrete mixed design.
Okay, ma'am.
So that's this one no objective of your work.
Yes.
No?
Yes.
When you didn't do the test on this one.
No, ma'am.
Paving block.
No.
That also you have to. Obviously, if we get the compressive strength of that concrete is quite okay, we will get the compressive strength for the paving. Okay, Steve.
Thank you, ma'am.
Thank you, Mr. Steve. The next presenter is Ms. Chinnu Mariam Nainan, paper ID 549.
All. First of all, thank you for giving me an opportunity to have this presentation. I'd like to have a review on the factors influencing the design of test methods for assessing acid attack in concrete. I'm Chinnu Mariam Nainan, research scholar at TKM College, Kolkata. Concrete is one of the most commonly used and economical construction material. One of the major causes of deterioration of concrete is acid attack. When we see the mechanism of acid attack, concrete is highly alkaline, whose pH is about 12.5. When it comes in contact with an acid, it disturbs the chemical equilibrium of cement matrix, altering the hydrated products, leading to microstructural deterioration. This affects the strength, durability, and structural integrity of concrete. Currently, there are no standard procedures to assess acid attack. The tests currently adopted are chemical tests, where chemicals synthesized acids are used in the laboratory to study the effects. Microbial simulation tests, where active bacteria is cultured in the laboratory to study their effects. And in situ tests, where an actual structure which is directly exposed to acid attack is studied. Objectives of the paper. This paper highlights the need to develop standardized test methods for assessing acid attack. To develop such a method, we should have a clear knowledge about the factors which influence the selection of test methods. This paper classifies these factors as test condition related factors, which incorporate the settings and arrangements required for the study. Then the specimen related factors, which deals with the specimen used for the study, and acid related factor, which deals with the aspects of acid other than material properties. First, let's see the test condition related factors, which primarily deals with the testing environment. It can be either real condition in field or accelerated condition in laboratory. In field, the concentration of acid exposed will be very much lower. So we need very sensitive deterioration detection equipments to get the results. After getting the results, it should be properly extrapolated to predict the future. If we are doing it in an accelerated condition in laboratory, these test conditions can be accelerated by various means, such as increasing the concentration or providing greater surface area, etc. Thereby, we'll get better results in less time. More results can be obtained, so it is preferred by the researchers. These are the factors. Let's see each in detail. Test simulation condition. Depending on the field condition to be simulated, it can be either static, where there is no change occurs, or dynamic, where the test condition frequently changes. Then there is replenishment of acid solution. Either we need not have to provide renewal, that is no renewal of acid, or we can renew. It can be done either by constant renewal. We can do it either using constant replenishment method or automatic titration method. Also, we can periodically maintain, that is, we renew the solution after a fixed period by keeping the pH constant or pH within a range. Third factor is alternate drying and wetting. It is used to assess the physical effects on concrete, and the degradation is accelerated by capillary suction. The mechanism involves dissolution and crystallization of reaction products. Then there is effective abrasion, the process of removing loosely packed particles attached to the surface of the specimen. It can be either degraded layer or the precipitated salt thereby exposing new surface for chemical attack. It can be done using wire brushes or pressurized water jets. Both these enhances rate of degradation. Next factor is type of attack expected to occur at the field. It can be purely chemical attack which simulates the condition of submerged zone of effluence. Then there is combined physical and chemical attacks which simulates the condition of silos or concrete floors, etc. Then there can be combination of physical, chemical and mechanical attacks. It is usually the animal houses where there will be abrasion by the animal, etc. Then the factor required is focus of the study. What we actually have to study. For studying kinetics, the following parameters have to be considered. For studying mechanism, degradation mechanism, microstructural characterization techniques like XRD, XRF, SEM, etc. can be utilized. For identifying the suitability of a particular material, material properties, compatibility of the material, degradation kinetics and mechanism should be studied. These are the degradation measurement techniques which should be adopted for developing the test method. Next is initial curing in saturated lime water solution. If you are providing initial curing in this, it increases the compressive strength of concrete and prevents leaching of calcium hydroxide. It improves the permeability and better durability can be obtained, thereby reducing the rate of degradation. Next factor is temperature of the medium. Rise in temperature causes two effects. It can enhance the chemical kinetics of acid, thereby increasing the rate of reaction and rate of degradation. Also, rise in temperature causes the water in the pores getting evaporated, thereby increasing the porosity and permeability, thereby reducing durability and enhances rate of degradation. In both ways, degradation is enhanced. Now moving to the second section, specimen related factors. The first one is surface area to volume ratio of specimen. As the contact surface area increases, more surface is exposed for chemical attack, thereby enhancing the rate of concrete deterioration. For a given volume, area can be increased by changing the shape, that is providing a cylindrical shape, or by changing the nature of specimen. That is, if you are powdering the specimen, in both these cases, deterioration can be increased. Second point is type of specimen used. We can either use paste specimen, concrete specimen or mortar specimen. Generally, paste specimens are preferred for deterioration analysis. It is mainly because the acid attacks the paste phase of the concrete, not the aggregate phase. So, it is convenient to study the kinetics and mechanism in paste specimens. Also, it is possible to quantify uniform deterioration because there is no disruption by the aggregates. Also, in chemical analysis, usually aggregate complicates the process. So we need to extract the aggregates before doing the analysis. But if we are using a paste specimen, it can be avoided. Also, for microstructural characterization, the peaks of siliceous aggregates are generally very much higher in density than that of the cementitious matrix. So the results obtained can be misinterpreted easily. That can be also avoided. But the disadvantage of paste specimen is that we do not know whether it is a representative of real condition. For that, concrete specimen can be utilized. Also, concrete specimen helps to assess the effect of ITZ, interstitial transition zone. Then there are mortar specimens, which is used to quantitatively analyze the suitability and performance of materials. Next factor is shape of the specimen. Shape can be cylinder or cube or prism. Generally, cylinder specimens are preferred for strength test rather than prismatic specimens, mainly because of the presence of edge zone. Also, rate of reaction will be higher for cylinder, but we use prismatic specimens because it can be cut into smaller specimens for microstructural characterization, as shown in this figure. This specimen can be cut into smaller pieces, and each of these can be used for microstructural study. Then there is size of the specimen. All sizes can be used for the analysis, provided that a homogeneous significant attack zone can be identified in each. Smaller specimens give higher rate of deterioration. Even though it is like that, we prefer it for the experimental work, mainly because it requires only lower material and lower acids. also we get higher results. Next is nature of the specimen. Nature can be either solid specimen or a powder sample. Solid specimen, as already said, it can be either cube, cylinder, or prism. And analysis of mechanical properties and degradation kinetics can be done. Degradation of zones of degradation can be easily distinguished. If we are using powdered, it is obtained by crushing these solid specimen and used for microstructural characterization. Different zones of degradation can be separately chipped off and powdered to get the characterization of each zone separately, and it shows higher rate of degradation. Next is acid-related factors. First is concentration of acid. As already said, in realistic condition it is low, and in accelerated condition it is very much higher and provides higher rate of degradation. This is a graph experiment done by Dyer related to the mass exposure to acid attack. It shows that same miner may behave differently when exposed to both lower and higher concentration of the same acid. Next is interchangeability of acid. Certain acids cannot be used for experimental studies, mainly because it can be malodorous, or it is toxic, or it can cause irritation, corrosive, etc. So it can be substituted with another acid having similar effect on Siemens metrics in terms of their aggressiveness and degradation mechanism. An example is shown here. Butyric, isobutyric, and valeric can be substituted with acetic acid because they have comparable pKa value and solubility of calcium salts. Next is volume of acid solution to the specimen. As the volume of acid solution increases, it does not cause any change in the pH but increases the aggressiveness of the acid, thereby rate of deterioration. Next is acid exposure period. If there is no replenishment of acid, degradation increases till it attains a steady state. That is, all free anions are used to produce salts or complexes. Till that, degradation increases. But if there is acid replenishment, the degradation increases continuously. This is the summary of the paper. Concluding, the immense exposure of concrete to acidic environment highlights the need to develop a standardized test methods for assessing the same. To develop such a method, first we should have a clear idea about the factors influencing, and these factors can be broadly categorized into test condition related, specimen related, and acid related. The ranking of acid resistance could vary based on the factors chosen, and this needs further study. These are my references. Thank you.
The session is open to the chairs for questions.
Okay. How does the shape of the specimen? You have specified something about the shape of the specimen for studying these microstructural studies. How does this shape affect this study? Can you hear me?
Tinnu, are you there? Tinnu, you can chat the answer. If your audio is not visible, maybe some net issue. You are not audible, Tinnu. I think her connection is low. So let me check. Tinnu Naina is there. Then Tinnu, you can chat. Okay, you answer that one in your chat section. Did you hear the question? Anjana ma'am's question. Okay, usually prism and cubes and cylinders are used for the testing of the.
Okay, Sina.
Then prismatic specimens have edge effect.
Okay. Okay, Sina, you can continue.
Tinnu, you have presented a very good topic and you presented it nicely. Okay, Tinnu, you can stay over here now. Moving on to the next presentation.
Thank you, Ms. Jinnu. The next presenter is Mr. Pradeep P, paper ID 49.
Good morning, all. Myself, Pradeep P. Presenting paper in Seaside 2020. Paper ID is 49. The title of my presentation is Study on the Effect of Syndiate Fly Ash Aggregate and Steel Fiber on the Properties of High Performance Concrete. As an introduction, we know high performance concrete is a concrete having high or medium strength, low permeability, resistance to freeze and thaw actions, resistance to chemical attack, high to medium workability. Sectional curing will be less effective due to the low permeability of high performance concrete. And coming to internal curing, this type of curing is curing of concrete from inside out. It eliminates much of the uncertainties of external curing. Internal curing enhances the desired characteristics of high performance concrete by using pre-wetted or pre-soaked lightweight aggregate. Also, super absorbent polymers can also be used for this type of internal curing. This study incorporates the internal curing by using pre-soaked syndiate fly ash aggregates. It can be used in mixes with relatively low water-cement ratio. Disposal of fly ash is necessary for environmental conservation. Here, the internal curing is achieved by partially replacing the coarse aggregate with equal volume of pre-soaked pelletized fly ash aggregates. Aim of my study is to evaluate the strength, durability, and fractional parameters of internally cured concrete using syndiate fly ash aggregates and steel fibers. Objectives are to obtain the optimum replacement percentage of pelletized fly ash aggregate with steel fibers, to obtain strength and durability parameters, to determine the flexural strength and deformation characteristics of RCC beam incorporated with syndiate fly ash aggregate and steel fibers. Methodology incorporates first on literature review, then collection of materials, study of material properties, casting of the specimen, design mixed proportion, obtaining the optimum percentage of replacement, then by testing the specimen, then interpretation of the results. Materials used are OPC 53 grade cement, fine aggregate passing or 0.75 mm, coarse aggregate passing 20 mm sieve, syndiate fly ash aggregate having a size of 8 to 16 mm, silica fumes, super plasticizer used is Conplast SP 430, steel fibers are hooked with length 30 mm and diameter 0.5 mm. The minimum strength of concrete desired strength grade was M35. Water cement ratio used 0.38, cement content is power of 100. Fine aggregate for basic mix is 702 kilogram. Coarse aggregate 1230 kilogram per meter cube. Mixed proportion is 1:1.83. 3% of silica fume is added by weight of cement. Then pre-soaked syndiate fly ash aggregate is added to concrete by replacing 5, 10, 15, 20, 25 and 30% by volume of coarse aggregate. Again, steel fibers is added at 0.5, 0.75, 1, 1.25, 1.5 and 2% by volume of concrete, keeping 20% fly ash aggregate as optimum replacement as coarse aggregate because 20% replacement gave the maximum strength. Test on fresh concrete, the desired slump was 80 mm and compaction value of 4.9. So, for a water cement ratio of 0.38, 1.2% of super plasticizer gave the desired result. Preparation of concrete specimen, I have already explained different proportions where syndiate fly ash aggregates were used to replace coarse aggregate and it was designated as M0, M2, S5, that is 5% replacement by syndiate fly ash aggregate, X2, S10, 10% replacement by syndiate fly ash aggregate, like that up to M2, S30. The curing conditions were, all the specimen were including normal concrete were cured for 7 days in water and followed by air curing in room conditions. till the day of testing, that is 28 days, to simulate the actual site curing practices. Optimum percentage is obtained by testing the concrete after 28 days. Result and discussion. From the table, it can be seen that compressive strength result for replacement of coarse aggregate by fly ash aggregate, 20% replacement Sindac gave a maximum strength of 59.72 Newton per millimeter square at the end of 28 days. So that was the maximum strength that was taken as the optimum replacement of Sindac. The increment is 26.7% compared to normal conventional concrete. So the 20% aggregate was the maximum compressive strength, so it was taken as the optimum, and that was maintained, that proportion was maintained for further testings. Again, with 20% Sindac aggregate concrete, different percentage fibers were added, and 1% additional fiber gave a maximum strength of compressive strength of 63.46 Newton per millimeter square at 28 days. So the 1% fiber was kept as the optimum percentage. So that increment was 6.2% higher than the fly ash aggregate concrete, that is Sindac concrete, and compared to normal concrete, the increment was 33.5%. Split tensile strength increased up to 1.5% replacement, addition of fibers. Modulus velocity obtained are for normal concrete is 3.31 into 10 raised 4 megapascal. M2S20 it is 3.62. M2S20 F 1.0, that is 20% Sindac, 1% fiber, 3.74 into 10 raised 4. So the modulus velocity increased 9.36% when Sindac was added, and again it increased by 3.31% when 1% steel fiber was added. These are the durability tests. First one, water permeability test. These are the test arrangement. This one, this is the after the testing, the cube was split into two, and this is the marking of the penetration of the water. The maximum depth of penetration obtained for normal concrete is 28.7. 20% Sindac concrete is 25.9, and 1% fiber with 20% Sindac is 29.1 mm. According to DIN standard, that is German standard 1048 part 5 criteria, depth of water penetration is less than 30 mm. It can be used in, or it can be used in aggressive environment, and less than 550 mm can be used in water gradient section. So all the three types of concrete can be used for both the conditions. So it can be considered as a high performance category. Next is rapid chloride penetration test as per ASTM C1202. This is a test arrangement, and this is the time versus current versus time passed for 360 minutes. You can see both the M0, that is normal concrete, as well as 20% fly ash, Sindac fly ash concrete. Both the graphs are almost same. And fiber reinforced concrete cannot be used for testing, as it may, the conductivity of the fiber can affect the instrument. From the total charge passed calculation, the total coulombs passed for normal concrete is 1446.3 coulombs and 1476 coulombs for 20% Sindac concrete. So as per RCPT classification criteria of ASTM C1202, both the concrete have charge passed between 1000 and 2000 coulombs. This comes under low chloride ion permeability category. So again, here also both the concretes satisfy the high performance category criteria. This is a flexural behavior setup. The total length of the beam is 1.2 meter, width is 150 mm, depth is 200 mm. 3 12 mm bars are used as tensile reinforcement. This is a load versus deflection at mid-span of RCC beam. You can see normal concrete as well as Sindac concrete show almost same type of deflection properties, whereas this one, that is the steel fiber added concrete, showed much less deflection for the same loads. That is the advantage of adding fibers in concrete. So here we can see the addition of sintered fly ash aggregate has not affected the deflection properties of the high performance concrete. So that is not anyway defective compared to the other concrete. Again, maximum load carrying capacity increased from 140 kilonewton for normal concrete to 150.6 kilonewton for Sindag added concrete, and again it increased to 165 kilonewton for fiber added concrete. So the increment of fiber reinforced Sindag concrete is 7.6% compared to fly ash aggregate concrete beam, and it is 17.9% higher compared to normal beam. Flexure strength for M0 beam is 23.3 Newton per millimeter square. 20% fly ash aggregate beam is 25.1, and for fiber reinforced beam is flexure strength is 27.5 Newton per millimeter square. Scanning electron microscopy analysis shows that here we can see this is a distinction between the aggregate as the cement paste phase. The intertransition zone is clearly visible in zoom images, whereas this is the zoom image for Sindag and paste phase interface. Here this is the aggregate, fly ash aggregate, and this is cement paste. There is no transition zone is not clear because the cement paste infiltrated into the pores of the fly ash aggregate because of external hydration. Again, the hydration products, normal concrete crystalline structures are seen, whereas in enhanced curing, internally cured condition, spongy type images are seen, which shows that more CSH gel has been formed. It's a conclusion. Again, can be inferred that 20% of fly ash is the optimum replacement, and 1% steel fiber is the optimum replacement for highest composite strength. The increment in compressive strength is 26.5% when done normal concrete when Sindag, 20% Sindag was added. Then fiber, 1% fiber reinforced Sindag concrete, the compressive strength was 5.1% higher than 20% Sindag concrete, and it is 32.5% higher than the normal concrete. Split tensile strength also increased slightly when Sindag was added, and it increased considerably or very much when the fiber was added. Resistivity of fly ash to chloride penetration was very good, so it can be classified under high performance category. Also, water penetration depth is below 30, so it can be used for aggressive as well as water retaining structures. So it's again, as per durability condition, all the three concretes satisfied the high performance category. Flexure strength is 23.3 for normal concrete, 20% Sindag concrete is 25.1, and fiber add 1% fiber add concrete is 27.5. So there is the increment of 9.56 when Sindag was added, and 18.03 when steel fiber was added to normal concrete. Deflection of 1% fiber added concrete is very low compared to the other two concretes, whereas as well as the deflection is not affected when Sindag was incorporated. Same images I have already explained. IT sets, intertransition zone, is not clearly defined as the penetration of the cement paste happened in the Sindag fly ash aggregate. So the bond between the aggregate and the paste is very strong in the case of Sindag fly ash aggregate, and the more CSH has been formed due to enhanced hydration in the case of lightweight aggregate, pre-wetted lightweight aggregate at home. These are my references. Thank you all for the facial hearing. Thank you.
Session is open to the chairs for discussion.
Okay. See, how will you get this sintered fly ash aggregate?
So it is obtained from, I obtained it from Jindal Power Corporation at
Actually, powdered form, right?
yeah, it's powdered form. It is pelletized in rotary kilns. It is after pelletizing, it is fitted into rotary kilns, and up to 1200 degrees centigrade, it is heated, where it forms into a ceramic, round ceramic aggregate form, porous form.
Now, is it available in that form?
Yeah, it is available in the pelletized aggregate form only. Nearly rounded shape. It's porous, also lightweight.
Then what do you mean by this pre-soaking?
Pre-soaking means before adding to the mixing with the concrete, it is soaked for about 2 hours to ensure about 12% absorption, so that water absorption is not affected. The mixing water is not absorbed by this porous aggregate. So we soak it prior to mixing with water for about 2 hours.
Okay, similarly, by using this or by mixing about 2% of steel fibers, how can you mix that 2% of steel fibers and all?
So I tried up to 2, but it was very harsh mix, but 1% is the best result.
Okay.
So it's a manufactured aggregate, no?
Yes, ma'am.
Sintered fly ash. Now, what about the properties of this aggregate? Is it matching with our natural sand or M sand?
No, it is a coarse aggregate. Size is
Coarse aggregate. Oh, okay.
Only crushing strength is less compared to the normal aggregate.
What about the specific gravity of this sintered fly ash aggregate?
Specific gravity is very less. It is only about 2, nearly 2.
So it's a lightweight one now.
Lightweight one. Only thing is crushing strength is less compared to normal aggregate, but it satisfies the highest condition that the crushing value should not exceed 40.
So we can't use this for the reinforced concrete work because the gravity is very less, no?
We can use it. It will give a lightweight concrete as well as this indium curing will increase the strength of the concrete.
Okay, what about the density of this one, concrete, lightweight concrete by using how much density?
Yeah, when 20% replacement was made by using lightweight aggregate, the density decreased by about 9%.
What is the optimum value?
20%.
20%.
Above that, only the strength decreases.
Okay, Pradeep, your presentation is good. Next, we will move on to the next part.
Thank you.
Thank you, Mr. Pradeep. Our next presenter is Ms. Arya E.K., paper ID 172.
And Arya. The last one. Research scholar from RIT College. I'm presenting my paper Pollution Control of Reinforced Concrete Structure in Construction Industry, RIT. As you know, concrete is the most commonly used construction material. It is strong in compression, but it is weak in tension. In order to compensate this weakness of concrete in tension, steel rebars are embedded in concrete. The RC structures, which are designed for more than 300 years, are seen to get deteriorated even in less than 10 years, and corrosion of steel reinforcing bars is considered as a major reason behind this. So let's see what is the science of corrosion in reinforced concrete structures. The concrete has an alkaline nature and its pH is greater than 12, which makes a passive layer on the surface of rebars, protecting the steel rebars from external environment. But when chloride ions from the external environment gets into the concrete and hits the passive layer, Certain chemical reactions happen on the surface of steel rebars, giving rise to Fe2 plus and OH minus ions, which is nothing but the anodic and cathodic reactions, and together producing the corrosion products. And this corrosion products occupies a volume of almost 4 to 6 times the volume of the original steel, and there are many negative effects associated with that. So let's see what are the impacts of corrosion. The first one is the potential risk of rapid structural failure. As I said earlier, due to the high volume corrosion products, it induces tensile stresses in the concrete near to the rebars, giving rise to these cracks. These cracks propagate and adversely affect the concrete structure. So this is the structural impact of corrosion. Next is the economic impact of corrosion. According to the study conducted by NAILS in 2016, it showed that 15% of the newly constructed bridges are structurally deficient due to corrosion. It contributes about $276 billion per year, and the indirect cost of 10 times that of this direct cost, together having 3% world's GDP, which is very huge. So due to this structural, economic, aesthetic, and other unmentioned impacts, the corrosion need to be stopped or controlled. There are so many control measures which is adopted nowadays in construction site. So in this presentation, I'll be reviewing the corrosion control measures in reinforced concrete structures, and I'll be identifying the corrosion control technique which is more suitable nowadays, and will be explaining its working, design, and installation. So first, let's see the traditional approach, that is the patch repairing. Patch repairing is the conventional and the most commonly used practice. So once the corrosion stains are observed on concrete surface, first we remove the damaged concrete where the stain is observed, then the corroded steel surface is removed and it is made rust-free. Then the repair mortar, which is commercially available, will be mixed with water and will be applied as patches. Now, according to literature, this patch repairing is just the covering of corrosion, and it is not a technique of protection from corrosion. And this is due to the effect known as halo damage. Halo damage is nothing but the formation of this incipient anode. Now I'll explain what it is. When a patch is applied on the surface, this is a new concrete and this is an older concrete. So through this older concrete, again the corrosion can trigger, and here this portion of the rebar can be formed as the anode, and this becomes the cathode. And then again it should be removed and it should be again patched. Then the upper portion will be again getting damaged, and that will be acting as anode, and this process continues and progressive corrosion occurs. So nowadays, this patch repairing is not adopted in site, as both clients and contractors have realized the outcome of this method because it worsens the situation. And the next thing is rebar coating. Rebar coating is nothing but coating the rebars with some products. And the most commonly used coatings are fusion bonded epoxy and cement polymeric composites. Both are organic polymer coatings, and all these coatings can trigger the corrosion if it is inadequately applied in site. In site, if the coated rebars are dented or dragged, if it is exposed to terrestrial sunlight, or if it is exposed to rainwater for a long time, or if the coatings are applied on rusted steel surfaces, it can trigger the corrosion. And one such example is shown in this figure. It is taken from the literature of Kambi Delay in 2020. So here, the invested steel rebar CPC coatings are applied, and I'll zoom out this image. So here we can see inadequate coating in these joints. So the remedy is that in order to ensure proper protection by rebar coating, we should apply the coating prior to the caging, and the surface of the rebar should be properly sandblasted, or the surface should be made clean before the coating is applied on the steel surface. The cathodic protection system, it is the most common method that is available nowadays. In cathodic protection system, it controls the corrosion of steel by making the steel work as a cathode in an electrochemical cell, the concrete will be the electrolyte, and an anode will be there, which is an external anode will be installed. And the connection and the activation of the anode will be marking the difference between the two different cathodic protection systems, that is the ICCP system and the SACP system. In ICCP system or the infrared current cathodic system, we use the inert platinum anode. So in order to activate the platinum anode, an external current will be required. But in SACP system, zinc anode will be used. So in electrochemical series, when compared to steel, zinc is on the upper side. So zinc will corrode, zinc will sacrifice itself and protects the steel. Here, platinum will corrode with the help of the external source. So that is the main difference. Now let's see what is the other difference. So in ICCP system, since platinum is used, more life expectancy will be there, but more costly. And in SACP system, it will be having a finite lifespan, but no problem if the life expectancy of sacrificial anode is finished, it will be removed and a new sacrificial anode will be installed and it will be patched up. But there are many disadvantages which are associated with ICCP systems, such as alkali aggregate reaction, bond strength reduction, hydrogen embrittlement, and it cannot tolerate the vibrations during the installation. Like if a bridge needs to be repaired using ICCP systems, the whole traffic should be stopped because it can't handle the vibrations which is caused due to the movement of the vehicle. So, but in SACP system, no such issues are there. It can handle. And in ICCP system, it has bulky equipment, so it can change the profile, loading, appearance, and clearance of the structure. In ICCP system, no external power source is required, minimum monitoring is required. So in buildings such as Rashtrapati Bhavan or in confidential buildings, ICCP system is mostly recommended. And low risk of cathodic interference with the adjacent structures are also there. Then it is easier to design and install. So due to all these advantages, and it's also less cost. Approximately 1% of the total project cost will be only there for this repair mechanism. So SACP system is the most recommended one. Next, we'll see what a sacrificial anode looks like. So in a sacrificial anode, we have these tie wires. The tie wires are used to tie the steel rebars for electrical connectivity with the zinc or the anode. So it has anodic metal, that is the zinc, and the encapsulating motor which is surrounding the metallic core. And the encapsulating motor is very important because it has two major properties. One is the high alkalinity of the encapsulating motor, and other one is the high porosity. It should have high alkalinity to promote the anodic dissolution and provide steel galvanic protection against corrosion, and high porosity should be there to accommodate the corrosion products and to ensure that no stresses of any kind arise around the metal core to initiate the reaction. So next is the design of anodes. The anodes are designed based on the design concept for buried pipeline. So it is adopted by the researchers in civil construction, and they have designed an equation for total weight of anode required by calculating the practical energy content. And from this total weight of anode, we can assume shape and geometric dimension, and thus spacing and number of required anodes can be defined accordingly. Next is the installation of anode. Many researchers have put forward or proposed certain installation guidelines for sacrificial anodes. In field, the contractors and or engineers have installed them in accordance with the studies which is conducted in either lab or in simulation software such as COMSOL or ANSYS, etc. Some installation guidelines are as follows. That is, one is the complete removal of the contaminated concrete all around the rebars to ensure a sustainable repair. The second one is the length of the patch should be greater than the corroded length of the rebar. This is to guarantee the load capacity of the patch. The third one is the embedment of the sacrificial anode should be in the substrate concrete and not in the patch area or in the repair area. If it cannot be done, it should be around the perimeter of the patch as shown in this figure. Now moving to the conclusions. The corrosion protection is a need of the decade due to all its structural, economic, environmental instability concerns. In traditional methods, patch repairing should never be adopted. Coating for rebars can be adopted only if proper site invigilation can be done. And the best method identified is that of sacrificial anode. Its design and installation is very simple and it is proved to be effective for uncoated rebars. But for structures with coated rebar experiencing corrosion, further research needs to be done and we should understand the mechanism behind the working of SCCT and coated rebar system. So that is the gap identified. So these are the references. Thank you for your attention.
Anjana ma'am and Seena ma'am, any questions?
Okay, Arya, you have presented it very nicely.
Thank you, ma'am.
Out of the various corrosion protection methods, which one is more reliable?
I think it is better for the contractors to carry out patch repairing, but the researchers as well as the clients have realized its disadvantages. So nowadays, along with the patch repairing, they are adopting for sacrificial anodes. I think it is more reliable nowadays.
What about the cost of that?
There is a myth behind that, like the cost of sacrificial anodes will be very huge, but when analyzed, when a proper cost analysis was done, it was identified that only 1% of the total project cost is only contributing to this repair mechanism. So it is not a big amount. Only 1% of the total project cost will be there.
Increased, okay. Okay, thank you. Seena, you can proceed.
Arya, you presented well.
Thank you, ma'am.
So this one corrosion control, what are the different corrosion protective method nowadays, most popular one?
Yeah, that's what I have explained. The most popular thing was, protection method was patch repairing, but we cannot stop by just repairing one side of the degraded concrete. So we have to continue if patch repairing is adopted, which is not at all feasible. And now the clients as well as the contractors have realized it and they have moved towards the sacrificial or cathodic protection side. So mostly it is now getting popular. And we are trying to look at that in India.
I mean in the research side.
In the research side, mostly the researchers have done their works in coated rebar system. That is not a protection mechanism, but it is a prevention of corrosion mechanism. That is for newly constructing structures. We are adopting. We have a concept that if the steel rebars are coated properly with this commercially available coating system, then the chloride ions from the external environment won't hit the rebar. So studies are happening there, but it is proved that it is not feasible because of the inadequate site practices, because we don't have trained practitioners in these sites. All are untrained local labor. So we can't completely rely on the coating system, but many researchers are happening in this coated rebar systems.
Okay. Okay, Sini. Okay, Arya. Move on to the Shruti compare.
This was the last presentation for the session 1, Experimental Mechanics. Thank you, Dr. Anjana and Dr. Seema ma'am for chairing the session. I also thank the participants for their active participation. Our next event is a keynote address by Dr. N. Ganeshan. Dr. N. Ganeshan was working as Professor of Department of Civil Engineering, and formerly he was also the Dean of Planning and Development at the National Institute of Technology, Calicut, India. He graduated in Civil Engineering with first class from Madurai University. He received his ME with distinction and PhD degree in Structural Engineering from the Indian Institute of Science, Bangalore. He was awarded Sir Vikar N. Chandavarkar Gold Medal by IIC Bangalore for the best PhD thesis in the year 1986. He has 40 years of experience in teaching and research. His research interests include concrete technology, reinforced concrete, ferrocement, fiber reinforced concrete, polymer modified concrete, and self compacting concrete, forensic engineering, and rehabilitation of RCC structures. He is a fellow of the Institution of Engineers India and consultant of International Ferrocement Information Center, Bangkok. He has guided 100 MTech theses and 25 PhD theses. He has also published more than 170 papers in the international and national journals and conferences. He was awarded E.P. Nicolaides Gold Medal for the best research paper entitled Behavior of Steel Fiber Reinforced High Performance Concrete Members Under Flexure, published in the Civil Engineering Journal of the Institution of Engineers. He was also awarded the Railway Board's prize for the paper entitled A Simplified Procedure for the Design of Machine Foundations Subjected to Vertical Vibrations. Both the awards were presented at the 23rd Indian Engineering Congress. He received the ISTE National Award for having guided the best MTech thesis in civil engineering at the 41st Annual Convention of ISTE held at Punjab on 16 December 2011. Recently, he received the ICI Ultratech Award for Outstanding Concrete Engineer of Kerala. Concrete Engineer of Kerala for the year 2014. He has conducted more than 30 short-term courses in the field of structural engineering and delivered expert lectures in several international and national conferences. Also, he has carried out several consultancy projects in civil engineering for government and private organizations. He was deputed by MHRD Government of India as a visiting professor to the Asian Institute of Technology, Bangkok in 2004. He was also the visiting professor at King Khalid University, Kingdom of Saudi Arabia in 2008. He is a reviewer of many national and international journals. He has also visited University of Dundee, Scotland, UK, Queen's University, Belfast, Northern Ireland, National University of Singapore, and University of Stuttgart, Germany, University of Michigan, USA, in connection with the presentation of papers and invited lectures at the international conferences and workshops. He will be speaking on studies on hybrid fiber reinforced concrete. It is my greatest honor to welcome you, sir, as a keynote speaker for today's conference.
Thank you very much. Thank you very much.
Welcome, sir.
Yeah, thank you. My voice is clear, audible?
Yeah, audible, sir.
Okay.
Sir, our HOD is here, Dr. C.
Oh, good morning. Hello.
Good morning, sir. Good morning, sir. Welcome, sir.
Thank you. Thank you very much.
Sir, we will move on to the presentation now, sir.
Okay. Okay. So, good morning to all of you, the delegates, research scholars, students, faculty members, ladies and gentlemen. At the outset, I would like to thank the organizers of this conference, Seaside 2020, for giving me this opportunity to speak in front of you on a very important topic, that is the studies on high performance hybrid fiber reinforced concrete. It's a very rapidly evolving topic and will be useful to many research scholars who are working in this area. So let me move straight away to my presentation. So once again, I take this opportunity to speak to thank all the people associated with this conference, especially Dr. Zina and others. So let me present the topic. I hope my slide is visible.
Sir, could you please make it in the slideshow?
Yeah, I put in the slideshow only. Is it clear?
Now it's clear, sir.
Yeah. Okay, so let me move on to the topic. Studies on hybrid fiber reinforced high performance concrete. That is what I want to speak. When we look at high performance concrete, we know that concrete is a traditional material used in the construction industry for the last so many years, more than 100 years. highly indispensable despite its inherent deficiencies. You know that concrete, which is very good in compression and very high moldability and all, but the major problem with this material, a very important material, is it is poor tensile strength and flexural strength and so on. Roughly, the tensile strength is about 1/10 of its composition. So, a lot of work is being carried out, and many scholars have worked in this area to improve the tensile strength of this composite, so that this could be comparable to that of the compressive strength. So, in this respect, many works have been carried out. The recent research by concrete technologists were aimed to enhance the service life. When I say service life, when you design ordinary concrete structure, for example, our own residential buildings, generally what happens that the building is supposed to give a life period of not less than about 75 years. Every now and then we cannot demolish and construct a building. In the case of bridges, we want more than 150 years, but unfortunately many bridges which are causing a lot of problems. Within a very short span, they are becoming useless and lead to rehabilitation, retrofitting. That is that you are coming across such problems in day to day. And in the case of hydraulic structures like dams, we want at least 250 years. So how to enhance the service life? To improve the resistance to penetration by external agents, improve the resistance to internal deterioration. All these things are the major topics, and concrete technologists are working in this area. When you look at high performance concrete, there need not always be of high strength alone. It should be of high resistance to unacceptable rates of deterioration. If somebody asks you a question, what is the life of a concrete structure? That depends on the rate of deterioration of concrete. If it deteriorates very fast, the life will go. So, if the high resistance to unacceptable rates of deterioration. According to the ACI committee, when you look at ACI committee, HPC is defined as a concrete meeting special combinations of performance and uniformity requirements that cannot always be achieved rationally using conventional constituents and normal placing and mixing and so on. So, there is, besides strength, certain specific performance requirements have to be met. Example, the precious concrete bridges, when you take not only high strength but reduced shrinkage and creep, that is very important in this area. Because if the shrinkage and creep is taking place, means the long-term effect will seriously affect such bridges. As a typical example, offer structures, airport pavement, machine foundations, everything should possess high fatigue strength. So there are specific requirements. Similarly, the nuclear containers, high resistance to thermal cracking, because the temperature will be very high. So that concrete should have a high thermal resistance. So generally, HPC means high strength, low volume of power. That means density should be very high. Particles graded down to the finest size. Mix must be sufficiently workable. That is also essential for the solids to be dispersed properly. Deflagellation so that dense packing is achieved. And for that, of course, we use superprocesses. The term of HPC was first used by Mehta and Aitken. Aitken has done a lot of work in this area, and they say that the HPC possesses three important characteristics. One is high strength, high workability, high durability. So the three items have to be properly taken into account. Thus, a primary distinction between high-strength concrete and HPC was the main mandatory requirement of high durability in the case of HPC. So, as I mentioned earlier, higher strength, improved durability and workability than conventional concrete. So, it requires, So it requires additional materials like fly ash, microsilica, and superprocessor to improve. So additional material like fly ash and microsilica to improve durability, because they will go and fill the entire what is called the forum and try to fill all the voids, micro voids are there, and they will try to fill and improve the density. And the workability will be of course improved by the superprocessor. and the strength will go up by reducing the water cement ratio, so we require the help of simple processor. And when you add materials like fibers, so when the fibers are added, that they improve many of the engineering properties like tensile strength, flexural strength, energy absorption capacity, ductility is very important. You may ask a question, what is the after all ductility of concrete? Because the concrete itself, when you apply load, it will start what is called creating some small cracks which will not be visible to our eyes at the interior of the structure. And slowly these micro cracks will merge into macro cracks and lead to problems. So ductility and crack control, shrinkage and structural crack control, both at the green stage as well as hardened state. Well, there are several types of fibers. For example, straight steel fibers, crimped, some sort of undulations are given here. Some sort of undulations. When you give this undulation, that will improve the bond between the fiber and the matrix. Or the hooked end fibers, there will be at the end there will be a hook type of structure like this. These hooks are there, and that will improve the bond. Then in the case of metal fibers, similarly in the case of other things like synthetic fibers, micropolypropylene fibers, glass fibers, and so on, they are called synthetic fibers. Mechanical properties, if you look at type of fiber, acrylic, so many fibers are there, and the equal diameter, density, tensile strength, modulus of elasticity, ultimate elongation, everything is given. When you look at these fibers, the carbon fiber, which is having a very high strength and a very high density and so on, followed by other fibers. Similarly, the non-metallic fibers, you can see polyethylene and coconut and natural fibers, so many are there. Now, let us look into the HPFRCC. This term is very important. What is after all HPFRCC? When you simply add fiber, can you call that concrete as HPFRCC? That may be the question. And let us look into that. What is HPFRCC? High performance fiber reinforced cement concrete. How is it different from other cement composite? This is the question. How is it different? High performance fiber reinforced cementitious composite HPFRCC are defined as ordinary FRCC that exhibits post-cracking strain hardening response accompanied by multiple cracking. This is very important. Then only we call that as HPFRCC. Otherwise, that is not HPFRCC. In contrast, ordinary FRCC softened once the matrix crack. I will show you a figure. Ordinary FRCC will immediately soften. That means the strength will come down once the matrix cracks. But in the case of HPFRCC, even after the multiple cracking, the strain hardening property will be exhibited. Something similar to that of our steel. Okay, so let us look into the figure. When you look at this is an ordinary FRCC. That is a fiber reinforced concrete which is subjected to tension. There is a tension we are applying here, and the tension is applied here. Then what will happen? The stress, the diagram, you can see the diagram. Stress versus strain diagram. Till the first crack forms. The first crack forms somewhere here, and immediately after the first crack, the graph, you can see the material softens. That means it will come down. It cannot take further load. It simply comes down. Then that crack, there is only a crack. This is the only crack which is available and no multiple cracking. And this will soften the entire what is called material or composites, and the strain hardening is not exhibited here. On the other hand, come to this HPFRCC. This is HPFRCC. This is also subjected to loading like this. A tensile loading here. So what happened in this case, when you look at this figure, immediately after the cracking, the first crack is very important here. The first crack takes place here, then you have a multiple cracking. this entire area is a multiple cracking stage. And after the multiple cracking stage, there will be a lot of cracks. Something like a lot of cracks will develop like this. And one of the cracks will keep on widening and the failure takes place. So from that crack onwards, till that time it's called a strain. And from that crack onwards called a crack opening. The crack is opening, then the value will be higher. Then the strain softening takes place. So this is the speciality of HPFRCC when compared to ordinary FRCC. So always try to understand the HPFRCC, which has the ability to develop the strain hardening response as in the case of steel. That is why it is called engineered cementitious material. And we have to thank Professor Naumann and all for developing equation for such composites. And you see, this is HPFRCC with a lot of cracks here. There are so many cracks here. And one of these cracks, you see, finally lead to the failure of the car. So localization and the multiple cracks. And the such material we can call the material which exhibits strain hardening response could be called engineered cementitious composite. So I can define engineered cementitious composites, ECC. ECC is a highly ductile composite material with a tensile strain capability comparable to that of steel and controlled micro crack. That's also very important. That is having a crack width which is less than 16 micron, 16 to the power minus 3 millimeter. That means the 0.06 millimeter. That is 60 into 10 to the power minus 3. So millimeter we can say. So the value will be 0.06 millimeter. It's a very low value and you cannot see this crack. Normally the cracks will be visible when it is of the order of 0.1 millimeter. And the maximum width of crack as per Indian standards should not exceed 0.3 millimeter. If it exceeds 0.3 millimeter, that structure violates the limit state of crack width. Okay, so that is a limit to which we can go, and beyond that we have to find out the reason for the development of such cracking and so on. The excellent tensile strain capability of ECC is originated from the bridging effects of short fibers capable of transferring tensile stress after cracking, resulting in the formation of multiple cracks. So we want always ECC, engineered cementitious composite, so that composite develop multiple cracking. That means strain hardening response, and finally the softening takes place after the what is called widening of one of the cracks from the multiple cracks. So when you say the various factors which affect fiber concrete, the physical properties of fibers, size, type, elastic properties, aspect ratio and so on, volume fraction of fibers, concrete mixed properties. Then when you look at the conventional fiber concretes, only one type of fiber is generally added, only one type. The gradual and multi-scale nature of fracture in concrete implies that a given type of fiber can provide reinforcement only at one level and within the limited range of strains. So when you use only one fiber, what happens? This cannot fulfill several criteria like micro cracks, macro cracks and so on. So two or more types of fibers, when they are added to the high performance concrete, which makes an efficient material composite. For example, broadly recognized combinations are hybrids based on fiber constitutive responses. Hybrids based on fiber dimensions, short and long fiber, based on the fiber dimensions. When you look at the short thin fibers which bridge micro cracks, you can say the long fibers are here and short fibers are shown here, a smaller line, and the micro cracks are originating when you apply load. The short thin fibers bridge the micro cracks and increase the tensile strength of concrete. Then, once the micro cracks increases in width and length, what will happen? The long, thick fibers will come into picture. And the long, thick fibers bridge the macro cracks and increase the post-crack ductility. So, the addition of these two types of fibers which take care of the cracks at micro level and macro level. So, in spite of very dense microstructure and high compressive strength, the failure mode of HPC is because still brittle, because the high performance concrete is having a very high strength. You cannot have very high strength and high ductility, is impossible. So you can increase the ductility by using the other techniques like, for example, the external techniques like confinement and addition of fibers and so on. When you combine the characteristic of HPC such as high strength, low permeability, etc., with the improved crack bridging properties of hybrid fibers, an innovative material with improved tensile strength and the ductility, which in turn enhance the service level of the structure. That's what we want. So I would like to present very briefly the HPC of M60 grade concrete that is used to conduct tests for tension stiffening and cracking characteristics of HFR HPC, and to evaluate the performance of HFR HPC in the case of beam column joints. I have taken tension stiffening and beam column joints as the two important what is called structural applications. For that, as usual, the cement used was OPC, fine aggregate passing rivers and zone 2. Metal admixtures are used, that is a class fly ash from Neyveli Grain Corporation. Silica fume 920D, that is 92% densified. 920D means 92% densified. Elka microsilica they supply. Then chemical admixtures, high-range water deessers. Naphthalene based reciprocal transistor, which is SP430. Metallic fibers and non-metallic fibers, both are used. Crimped steel fibers and micro polypropylene fibers. So this is a crimped steel fiber which is having a length 30 millimeter, diameter 0.45, aspect ratio 66, and the ultimate strength is 800 megapascal. You know that the undulations are given in order to mainly improve the bond. And it's a very thin fiber, length of fiber 12 mm, specific gravity 0.91, diameter of fiber is 32 micrometer, 13 into 10 power minus 6 meter. So the small value, aspect ratio means the length by diameter, and the strength is so much. So the mixed design done as per the method proposed by Professor Aitken. And this is based on American Concrete Institute ACA 211.1 modified by Professor Aitken. Okay, and he has given a procedure. Based on the procedure, the material, the mixed design was done, and the quantity of materials have been obtained. Actually, it's in a worksheet. One can work with the once you know the specific gravity, density, and all these things, you can work out. And these are all the part of worksheet. So finally, the cement is so much, fly ash is so much, silica fume, then sand, coarse aggregate, water, and the super process. Everything in kilogram per MQ that has been obtained. And the variables considered in this study: crimped steel fiber, volume fraction 0.51%. And when you put 0.5%, how much quantity of fibers you are adding? So that also we have given fiber contents. 39.25 and 78.5 kilogram per MQ fiber. So one MQ mix, so much fibers have been added. And the polypropylene fibers, again, it is given the volume fraction because a very small fiber, 0.1, 0.15 and 0.2, if you add more, the concrete will be very harsh and you cannot work with that mix. Fiber content is about 0.9 kg, 1.35, 1.8. These are the main variables of the polypropylene fiber. And the specimen designation is given here. That depends on HPC and polypropylene fiber reinforced concrete only with the polypropylene steel when you add SFR, and when you add both, it is called HFR. So only polypropylene, steel, and hybrid. Well, as usual, The control specimens are tube, cylinder, and prism. That is called, it's not a beam specimen, it's a prism. Prism specimens and cylinder. This is for compressive strength. Again, this is for split tensile strength, modulus of rupture, modulus of elasticity. So many specimens have been done. And the values are which are given here, and you can always see that there is an enhancement with the addition of the steel fibers. But actually, what happens in the case of compression, you will not have much what is increase in the compressive strength of the concrete. Sometimes you will have a reduction in compressive strength. On the other hand, in the case of flexural strength and split tensile strength, there is a marked improvement with this the fibers, the hybrid fibers and single fiber or hybrid fibers. But if the fiber content is more than what will happen? That will lead to balling effect and reduces the strength. So this is similarly modular elasticity, GPA. Now let me come to a very important topic, that is the tension stiffening, because quite often we are using this term in the case of width of crack. When you calculate the width of crack, as per the code, as per IS 456 2000, when you calculate without our knowledge or indirectly we are introducing this factor, what is tension stiffening? When you may ask a question, what is the tension stiffening? Which is the ability of concrete to carry tension between the cracks. When you apply load, a fluctual type of loading, cracks are imminent. Nobody can prevent the formation of crack. When you apply load, after a certain stage, a crack will form. And what happens in between the cracks? The concrete has the ability to carry tension, which provides additional stiffness for a reinforced concrete member in tension. Generally, we neglect the concrete below the what is called the neutral axis. Actually, in fact, the concrete in between the cracks will offer a stiffening effect, and due to that, the strain in steel will come down. After all, the width of crack W is equal to average crack spacing multiplied by the strain, steel strain. So this steel strain will come down because of the tension stiffening. So we have to calculate how much the tension stiffening effect is there when you add fiber to the concrete, especially hybrid fibers to concrete. So appropriately we can modify our equations. But how will you calculate the tension stiffening effect qualitatively and quantitatively? Quantitatively, when you look at the tension stiffening effect, tension stiffening bond factor is quantified something like this. Then you see this is a bare steel member. That means when you apply a tension test on a steel rod, this is a steel rod. Then it's got a bare steel, and this is a straight line up to yielding, up to that this point is yielding. And when you have in the steel rod what is called surrounded by a composite, it's called a fiber, it's a composite, it's a member or composite. So this is a steel inside and it's a composite. So when you apply tension, what will happen? There is an increase in the value of the tensile response that you can calculate. That is, this is the bare steel and this is a member response. So this distance divided by the PCR value, that is called a tension stiffening bond factor in order to quantify the tension stiffening bond effect. So so many prisms, concrete prisms have been made with the 600 millimeter size, axially reinforced with a 10 mm diameter bar. So we have a 10 mm diameter bar here, and this is the prism. This is a prism, 60 by 60. Okay, then it was subjected to what is called tension test. So we just simply pull the steel here and here, tensile load will be applied. Once you apply tensile load, naturally the first crack will appear here as and when the tensile strength of concrete is exceeded. Subsequently, another crack will appear, another crack will appear. That depends on the spacing between the cracks and so on. We will come to that. So, various what is called the specimens have been fabricated, and for each case, 2 specimens have been done in order to have an average, in order to study the average effect. HPC with steel 0.51, and these are all polypropylene. Further, this is a mold used for making the prisms. And after the prism is cast, that is tested in a universal testing machine and with a LVDT. LVDT you can see here, this is the LVDT, in order to measure the elongation, and the crack widths have been measured using a microscope with 0.01 millimeter least count. Okay, 0.01 millimeter means we can't see that division with naked eye. We require a powerful lens, very powerful lens. So the axial elongation was measured using LVDT over a gauge length of 550 millimeter. Crack width was measured at different load intervals using crack width measuring microscope. Crack spacing was also noted. Now you see, this is a HPC specimen. This is polypropylene fiber reinforced HPC specimen. This is specimen with 0.5% steel fiber and varying values of volume fraction of polypropylene fiber. Here with 1% steel fibers and so on. But when you look at the HPC specimen without any fiber, that broke into so many fragments. Even they came out. You see, some of this has come out, and the specimen broke. And in the case of PFR HPC, you can see some cracks. But in the case of this hybrid fibers, both the steel and polypropylene, what will happen? Large number of finer cracks develop rather than a fewer number of wider cracks. Normally, when you ask a question in the class, will you prefer a larger number of finer cracks to a fewer number of wider cracks? Generally, a civil engineer or a structural engineer will prefer finer cracks, even though it may be large in number. But the wider cracks are very dangerous because they are the source of what is called potential source of corrosion. The harmful chemicals enter through that what is called the gap and leads to the corrosion, and that will be very dangerous, and the life of the structure will come down drastically. So in this case, you can see a large number of finer cracks took place in the case of the hybrid fiber prism. Now you see the axial load versus strain have been what is called drawn for bare bar, HPC, polypropylene, steel fiber, and hybrid fiber. You can see it's a bare steel, simply with a steel rod which is subjected to tension, axial load. Only a straight line which is coming here, and this point is the yielding which takes place here. And the HPC. When you have the bare bar, there is a steel inside and the HPC. And this is the polypropylene fiber reinforced HPC. And this is the steel fiber reinforced, all individual. And this response appears to be better. That is the hybrid fiber. That is this one. Okay. From that, you can calculate the bond factor using the equation PCM by PCR. So that we can say that the bond factor is higher in the case of a hybrid fiber when compared to steel fiber and so on. So we can always select it. So in this case, after the test, the first crack load, yield load, and all these things have been computed. When you see the first crack load, how will you define that? The first crack load is the load at which the first crack appears. That will happen when the tensile strength of the matrix, is exceeded. When you apply load, the stress will develop. When the stress exceeds the strength of material, the first crack will appear. Then, of course, the yield load slightly higher with the hybrid fibers, and number of transverse cracks slightly more in the case of in our specimen with the hybrid fibers, especially this range, and average crack spacing, that is also very essential, which is reducing as the percentage of fibers increases and slightly more. That means it will give a higher width of crack. Because I told you earlier that the width of crack W is equal to average crack width spacing multiplied by strain intensity. Now this is the bond factor which is drawn with a member strain. You see for various materials, HFR HPC, and you can see that the bond factor improves in the case of HFR HPC because the effect that the low volume, low modulus fibers will bridge across the micro crack and delays the propagation of such cracks. And when you use the high modulus fibers, again it will bridge across the crack and delay the propagation of crack, which in turn will result in the increase in the energy absorption capacity of the material. So that improves the bond factor. So axial load, this is axial load versus average crack width up to 0.3 millimeter only I have plotted because this is no use. After that it violates the limit state of cracking. Okay, this is all for the tension stiffening effects. Now, with reference to beam column joint, in any structure, the beam column joints are very important. Why I'm telling is beam column, when you have a tall building, when the tall building is subjected to lateral loading, the first casualty will be at the joints. You can draw the bending moment diagram and shear force diagram, you can find out the maximum bending moment will occur at the joints, the beam column joint. And if the concrete is cracked, what will happen? There is a chance that the cracked concrete may fall down unless it is confined. So what happens? The structural damage takes place and the major damage takes place in the beam column joint, and that will lead to collapse. On the other hand, if you can transfer some amount of movement from that joint to some other place, that is called a redistribution of bending moment, then that will stand. So when you confine the concrete by using proper ties, and when you add fibers, only in the beam column joint, not throughout the column, then the excess movement will be redistributed to other places. And due to that, the collapse can be prevented. So now look here to study the beam column joint behavior, load deflection behavior, moment curvature, energy absorption capacity, stiffness degradation. And so for that, about 12 specimens have been cast. The variables 0.5 and 1%, volume fraction of polypropylene fibers, so much. So this is the specimen reinforcement detail is for all the specimen. Only thing is here the steel fiber content and the polypropylene content varied, and these are all ties. The ties, everything remains same. These are all stirrups. That also remains same for all, and this is okay. These ties give what is called a confinement, and this is a specimen which was used for testing. And in order to measure strains, the strain gauges, electric strain gauges were attached to the steel bar and protected using Teflon material so that it will not be wet during concreting. And the leads are there through which we can disconnect it to a data logger and the strain can be measured. This is our testing frame. Everything, all fabricated in the laboratory, the loading frame, and using that you can apply load up to about 40 tons can be applied. This is a green color frame, and this is a steel beam, and this is a hydraulic jack, and this is a pump, and this is a load cell of about 50 kilonewton or 5 ton, and hydraulic jack, because we want to apply load in the upward direction as well as downward direction, so that it's subject to cyclic loading. Then we have the data logger for measuring the strains and the load indicator, so that measures the load which is applied. and the dial gauge, so that the deflections also, that is when you apply load, we are applying load on the beam element, the tip of the beam. And this is the joint and the displacement indicator. So this is what is called elevation, and this is the place where all the loading is applied in the upward direction as well as downward direction. Yeah, now you can see this is the specimen. You have the LVDT at the top and bottom. Measure the steel strain, that is the strain at this point epsilon C, and the strain at the bottom epsilon S, depending on the loading. Then for the rotation, measure the shear strains using the diagonal LVDT, and this is the arrangement. And when you look at the joints, as I mentioned, that HPC specimen, polypropylene specimen, steel fiber, and hybrid fiber reinforced concrete specimen, and in all these cases, when they are subjected to reverse cyclic loading, that is the load is applied, this is a specimen, the load is applied and it deflects, like this deflects, and similarly when you apply load, it will go. So reverse cyclic loading was applied, and you see that very fine cracks obtained in the case of hybrid fiber reinforced joints when compared to other joints. And this is the load deflection curve. That is a loading, unload. This is a loading, unloading, reloading, and so on. So you will be getting a hysteretic curve, and that is very important in the case of reverse cyclic loading. And using that, we can determine so many parameters, strain, degradation, and everything. So when you join the tip of all, you will be getting a curve like that. So using that, we can find out the first crack load and all these things, because we are getting a smooth curve and the degradation stiffness. So this gives a tabular form, which gives a type of loading which is applied forward cycle, reverse cycle, absolute displacement ductility factor, and relative ductility factor. And when you use this HPFRCC, the relative ductility factor, that goes up. Okay, and the first crack also, there is improvement. And of course, the ultimate load, there may be a slight improvement, but the first crack load, there is a good improvement which we get from 8 to 10.5 or 11, which is HFR HPC C5. And we are getting a ductility which is higher with 3.6. What I am telling is, when you add this hybrid fibers, that improve several engineering properties. Okay, the tensile strength will go up, that the first crack will go up, ductility will go up, all these things will improve. And this is the cumulative energy absorption capacity. And the stiffness of the joint gets reduced when the joint is subjected to cyclic loading. Once the crack comes, the stiffness will come down. The slope of the line drawn between the maximum positive displacement point in one half of the cycle and the maximum negative displacement point in the other half cycle is known as the secant stiffness. And using that, the stiffness have been calculated, and the stiffness comes down as the number of loading cycle increases. 5 cycles, 10 cycles, 5, 10, 15, slowly stiffness comes down. And in the case of what is called PFR HPC, when you take this specimen which is having a high stiffness, but slowly it is coming down. And this is one which is having that the HPC alone. Initially, this is the value. It comes, drastically it comes down initially and slowly comes down. So stiffness degrades. So initial stiffness will be very high with HFR HPC, and the reduction in stiffness will be very, very gradual. That is what we have to find out. Well, I don't know how much time I have, Dr. Sina.
45 minutes, sir, for the presentation.
So the time is over?
It's over, sir.
About over. Okay, so at this stage, I would like to stop my lecture. Of course, I would like to say something about the confined concrete. Whenever you want the ductility, the only solution is confinement. So when you have the confined concrete, in the case of tall buildings, for example, it's a tall building with a single bay, multi-story, let us say. The joints are there. In the joint, the beam column joint, when you have closely spaced ties, this, then this steel reinforcement is coming later. These ties will improve the ductility, the structural integrity, I can say structural integrity and dimensional homogeneity of the composite will be improved, and the what is called sparring of concrete will never take place. And because of that, the entire concrete will act like a single material, and that will redistribute the bending moment to other places like this. Okay? Then that will prevent the damage to the joints. They are very important. So that's what I want to convey. So with this presentation, let me stop my lecture. Of course, so many slides are there. I want to stop at this stage. And if you have any questions or clarification,
Okay, thank you, sir, for the
happy to.
Now it is time for all of you can ask your doubts here.
Yeah.
Question attendees can clear their points in the chat.
So questions from the participants? Participants? Sir. Questions from the participants? Any of the participants you can ask? Arya?
Oh, Arya is very specialist in this area.
Oh, her topic is corrosion control. Arya, you can ask.
Oh, yeah. Arya, are you have any clarification regarding whatever I presented now?
No, sir. The presentation was excellent. That's really understand.
Very good. Okay, very good. Thank you.
Thank you, sir.
So, if there are no other questions, well, I thank all of you, all the participants, for your patient listening to my lecture. I thank one and all, every one of you, including the organizers and the person responsible, Dr. Dina, who was requesting me to deliver a talk. And I thank every one of you for your kind attention. Thank you very much.
I would like to thank Dr. N. Ganeshan. I, on behalf of the coordinators of Insight 2020, extend my wholehearted gratitude to Dr. N. Ganeshan, who took the time to make this session very informative with his talk on studies on hybrid fiber input context. I thank him for sharing with us his knowledge and finding time from busy schedule to make this event extremely informative. This talk is important and very useful for all the students of civil engineering. Thank you, sir.
Thank you, Miss. Thank you.
Thank you, sir. Thank you.
Thank you, Miss. Thank you.
So let us conclude this session. Next section is at 1:30. We can join at 1:30 for the session 2. So Noel Varghese, Sajid Chandran, Glenn Mary Jacob, Nina Suku, and Alka Susan Matthew are the participants. And the chairs are Dr. Priyadarshini and Dr. Arun S. The next session starts at 1:30 p.m. So this is a lunch break. After that, all of you join at 1:30 p.m. Okay, thank you, participants. Join at 1:30.